Hello? Hi. I'm just gonna wait for a few more people to join. Um, I'm completely exhausted. Hopefully, I won't make too many mistakes today. Yeah. How's everyone doing? Hi. Hi, Robert. Hi, Candyman. Okay. Seems like we're online. Okay. Let me just. So, the plan is to do some mathematical statistics this evening. I haven't uploaded a mathematical statistic video for some time. The latest mathematical statistics video was uploaded before the channel got hacked, which was already a week old, right? Already a week ago before that was. No, the channel was hacked on the 1st of June. So it's 2 weeks ago. Okay. And since then, I have never uploaded a mathematical statistic video. So we're going to make up for that today and do some basic mathematical statistics. So hopefully I'm still familiar with this material, okay? I like to say I'm 90% likely, okay? Not 95% confident, okay? 90% confident that I'm familiar with this stuff. So without further ado, let's get started. In case you guys don't know, this book, Probability and Statistics, The Science of Uncertainty, second edition, is completely free. It's written by two professors from the University of Toronto, Michael Evans and Jeffrey Rosenthal. I think, I think if I'm not mistaken, Mike Evans is a big name in the stats community. So if we just go to this link, this is Professor Michael Evans, and you can see some of his, I guess, is that podcast on YouTube? Yeah, that's true. And this is his book. This one is not free, unfortunately. Measuring statistical evidence using relative belief. Huh. This sounds very Bayesian. Okay. But yeah, this is a big name in the stats community. And Jeffrey Rosenthal, he has written some very friendly, very approachable books. I apologize for the cell phone viewers because the text is rather small, but I do recommend two more books that Jeffrey Rosenthal wrote. Okay, so hang on. Yeah, he's written two books, which I'm more or less familiar with. One on stochastic processes, and one on rigorous probability. So this is perhaps the most user-friendly measure theoretic probability on the market. A first look at rigorous probability theory. Okay. This book is not free, but it's still pretty affordable. If you go to Amazon, actually, here's here. It's $33 US. And there's a free public online solution manual to all even number exercise. So yeah, this is graduate level probability that is written in a very approachable manner, and now with free solution manual, if that's something that you need. Okay, and this book, Stochastic Processes, the first look at stochastic processes, is also extremely approachable. And this book, I don't think it uses measure theory, but it covers the basics like Markov chain, renewal theory, continuous time Markov chains, and martingale, discrete time martingale. I think Brownian motion as well. So it's got lots of stuff, but the exercises are pretty doable, which I like a lot. It's very approachable and is based on a course at the University of Toronto called STA 447. So yeah, I strongly, and here's the content list. And this book is also not free, but it's affordable. It's $38. Okay. Once again, I get nothing from promoting these books. It's just the books that I found useful and more affordable, more affordable than average. Okay. Because I know, like, the textbook prices are ridiculous. It always has been. I mean, perhaps not always has been, but in recent decades, it's kind of ridiculous. Does it get to the time series? This book? No. I mean, usually time series are not covered in stochastic processes courses, okay? Unfortunately, this is just a tradition. If you get to the I mean, if you want time series, you might want to go to a dedicated time series book, which there's some quite good options actually. Let me inventive. Let me just find one for you right now. I think it's Introduction to Time Series and Forecasting. Yes, this one. So, like, if you're looking for a undergraduate level time series book, this is excellent. It's called Introduction to Time Series and Forecasting. Okay, so time series aren't usually covered in a theoretical stochastic calculus course. It's usually introduced in a time series course. Okay, time series course or something that title with a forecasting in the title. Here you will see the usual ARMA process and stuff. Listed in Discord for no, unfortunately not. I mean, I can do that for sure, but I figured the Discord server is not the best format for creating a literature reference, right? Because I mean, people discuss, which is good, but it can also get a bit chaotic. You know, I want these things to be easier to access and look up, right? So Wriggle mentioned Wrigglestat, a channel member. Sorry, not I don't think he's a member, but a long-term supporter of the channel. He suggested let's do a publicly editable Google Doc, right? Ego, yeah. So I think I'll do that. So this one is like my go-to choice for time series and forecasting. And okay, wow, there's a link here. I mean, I don't want to get into trouble with the publishers or my channel get demonetized. But this is, how should I put this? The authors, Brookwell and Davis, they wrote the standard graduate introduction to time series and forecasting, in which they prove everything. In which they prove, I mean, pretty much everything they wrote in the book. Okay, like it's heavily based on Hilbert spaces, like the functional analysis, because time series analysis, at least the classical time series analysis, is also L2 geometry. Okay, it's just a bunch of projections, and the foundation is Hilbert space theory. And this book is more applied. Okay, this book is more hands-on. It does not require any sort of analysis background. And even though not everything is proved here, it does provide lots of examples. As we go through this, we'll keep your geometry explanation. I really like those. Yeah, I'll try inventive. Yeah, I know. I'll because It's been a while since I uploaded the geometric approach to statistics series, right? I haven't uploaded anything recently. It's been over like 3 weeks or even more, which is a shame because I've been kind of occupied with the stochastic series and the um, what's that? The complex variables. So those two series needs to have like one video each just to keep up the momentum of the series and um, and there's a there's a video in development hell right now on uh, like the geometry of the sufficient statistics. So maybe you guys heard of that. It's called it's a fundamental concept in mathematical statistics called a sufficient statistics, and it's done geometrically. So that video is now unfortunately stuck in development hell. I'll try to put it out as soon as possible. So there's that. And yeah, I'll definitely try to balance things a little bit because right now I'm like a one-man department. um, okay. Yeah, hopefully I don't burn out. All right. Okay. Enough for the book recommendations. Um, I'm glad you brought up the time series analysis. Okay, this is an amazing topic, and this book is also very hands-on. I think um, it covers some stochastic calculus as well. So yeah, it's a great book, even though it's more elementary than the graduate version. Um, it's still yeah, you just need to know basic calculus, matrix algebra, elementary statistics, but it still needs some serious work to understand the examples. Okay. All right, enough for that. Let's look at the main topic today. So, this book, Probability and Statistics, The Science of Uncertainty, how should we evaluate this book? It started from probability. It started from basic probability, so it assumes nothing about probability. And I really mean that, okay? It's not just a review of probability and then dive into statistics. Introductory probability and statistical application. Yeah, thank you very much for your recommendation. Yeah, Tagila, ARG. As I was saying, I'll put up a Google Doc that is publicly editable, so everyone can add their book of choice or their recommended books on that list. Okay, and if you can provide like a one-sentence description, why do you recommend this? That will be even better, right? So, because I've been talking about these books for a few times now, right? It's not the most efficient way to recommend literature. So yeah, anyway, I was talking about this one. It really assumes nothing. Okay, so this is meant to be a first introduction to the subject, to probability and statistics. So it really starts from the fundamentals, probability model, random variables and distribution, expectation. So this is really for a first introduction of the subject. Okay, and the prerequisites is I think 2 semester worth of calculus. So you need to know how to calculate integrals and series. Okay, so that's the main prerequisite. I don't think you need any linear algebra, even though it will synthesize. It will synergize with the material. Okay, at some point, statistics is like 90% linear algebra. I mean, at least when it comes to the actual calculation. Here, not so much. The fundamental concept of statistics can be understood without too much linear algebra. But it is when you start to handle like a real world data set, especially bigger data set, that linear algebra is essentially the arithmetic of modern statistics. Okay. So in this book, you can still kind of get away with not having a linear algebra background. So it's pretty accessible in my opinion. So starting from chapter 4, sampling distributions and limits. So this is really building towards a theory of statistics, because there's a lot of convergence in statistics. In statistics, in most situations, I'm not saying all, but in most situations, interesting things happen when you have a large sample. Okay, for a small sample, you can still have interesting results. It is still possible, but that requires some additional assumptions, like the Gaussian distribution. Okay, typically speaking, if you have a Gaussian distribution in your assumption, most likely you will have some sort of closed form solution to your problem, which is nice for gaining intuitions and stuff, but of course more restrictive in applications. So most application in statistics relies on limits, relies on the limits of distributions. And this is a tricky concept because it's trickier than, say, the limit of a sequence of real numbers. Because a distribution really is a function, and it's a quite complicated one. A distribution is what? A distribution is what we call a measure. That's why in advanced statistics, you always talk about measures theory all the time. A distribution is a measure, is a way to assign a so-called size to a set. So it's a sort of function. A distribution is a function called a measure. And the convergence of measure is much more complicated than the convergence of a sequence of real numbers. So you end up with all sorts of, I mean, not all sorts of, but several major modes of convergence. For example, here you have convergence in probability, convergence with probability 1. So these two looks a little bit similar, right? But they are quite different. Convergence in probability, convergence with probability 1, also known as convergence almost surely, convergence AS. Okay, this is typically very strong. Convergence with probability 1 is a very strong mode of convergence. Convergence in probability is weaker. And the weakest of all is the convergence in distribution. But it's also perhaps the most applicable one. The most famous result in the convergence in distribution is known as the central limit theorem. You guys might have heard of that, the central limit theorem. It has endless variations actually. Central limit theorem is really a collection of results. Even though in this book we're most likely only going to see a classic version of it. And because of stochastic convergence or convergence of distributions, the limiting distributions, we can approximate the exact solution using numerical methods, and more specifically Monte Carlo simulation. Okay, so Monte Carlo approximation works because of some sort of convergence of distribution. Okay, I'm not saying convergence in distribution because that's a technical term. Some sort of convergence is needed to make Monte Carlo's approximation useful. Okay, Monte Carlo approximation, the simplest one being if you just flip a coin for a large number of times and you calculated the empirical fraction of getting ahead, okay, that's a Monte Carlo approximation. You're approximating the exact probability of getting ahead by the empirical frequency of observing ahead in a large number of trials. So that's the Monte Carlo approximation in its most basic form. Actually, why is measure the size of a set instead of magnitude of a line segment? Good question. How do I inventive. Let's just give some basic idea about measure. Okay, so and this is not going to be a full-blown lecture in measure theory. just to give a basic idea of what a measure is. The most basic version of a measure is, of course, the length of a line segment. And this is what we call a Lebesgue measure. Okay. So here, so you have 2 points, A and B, on the real line. The length of the interval, A to B, is of course B minus A. Suppose B is greater than A. Okay. Right. So this is an example of a Lebesgue measure. And if we write down the definition of a Lebesgue measure, it would be what? It would be a function, mu, that takes a subset of the real line, a subset of R, to a real number. That makes sense? Because so mu is I'll put it this way. So it should map subsets of the real line to a real number. You're assigning a size to a subset of real line. And the first thing it needs to satisfy is that it needs to agree with the usual notion of length when mu applies to intervals. So for all A less than B, such that, okay, it needs to satisfy a bunch of properties. For all A less than B, what? Mu of A, B equals B minus A. Okay, it needs to agree with the usual notion of length. That's the first thing. Okay. And second, it needs to satisfy the translation invariance property, which sounds quite fancy, but basically it says, okay, if you shift a set by a fixed amount, okay, if A plus X, A is a set, A is a subset of the real line. If you shift that by X, it should not affect the Lebesgue measure. Does that make sense? Because you just, if A is a subset of real, and if you just shift it, okay, A plus X is what? Where A plus X is defined as the elements of the form A, little a plus X, where little a is in big A. Okay, so there's that. And second and third, it needs to satisfy, if I recall correctly, by the way, for all of these details, you can go to Axler's book on measure theory. Probably more accurate than this one right now, because I haven't prepared a lecture in measure theory for quite some time now. But basically what it says is, if you have a list of sets, A1, A2, all the way to AN, and so on, and so on. So this is an infinite list, or a sequence of sets, which are subsets of the real, which are disjoint, pairwise disjoint, pairwise disjoint. So they're pairwise disjoint, and it needs to satisfy this very intuitive property. So if you have a pairwise disjoint sequence of sets, the measure of their union should be the infinite series, that is the sum of all the measures. Okay. It needs to satisfy these properties. So why is the measure, so to answer your question, why is measure of the size, the measure of this, why is measure the size of a set instead of the magnitude of a line segment? Well, as I said, the measure is a function that takes a subset of the real to a real number. And when this subset takes the form of a line segment or interval. It agrees with the usual notion of length. Remember, intervals are only a very restrictive class of subsets of the real. Subsets of the real can be highly complicated. For example, the set of rational numbers. Right? The set of rational numbers is clearly not an interval. Now, the measure theory wish to discuss, for example, the size of the rational number. And from real analysis, it is a fact that rational numbers are countable, whereas the real is uncountable. So the both are infinite sets, but somehow rationals are of a smaller class of infinity compared to the real line. So when it makes sense to say the size of the rational is much smaller than the real line, right? So we wish to assign a big measure to things like the set of rationals, the set of irrationals, and all sorts of crazy subsets of real. But the interesting part is, it turns out that the goal of assigning all subsets of real a measure is too ambitious. It simply cannot be done. Okay, so if we wish to keep these intuitive principles, intuitive axioms, then it turns out that we cannot, good old Cantor diagonalization argument, exactly. So we're showing at least two things. The rational is countable and the real is uncountable. Okay, there are different methods to, there are different ways to apply the diagonalization argument. It's actually extremely powerful. The diagonalization argument in analysis shows up in several important proofs of several important theorems, and also the Gödel's incompleteness result in logic is also essentially a Cantor's diagonalization argument. Yeah, so very cool stuff. But the bottom line is, it turns out that here I did not say what kind of subset. I did not say what kind of subset. The initial goal is to assign all subsets of the real, a size. Seems like a reasonable project. Right? Seems like totally reasonable. So you pick an arbitrary subset of the real, we wish to give a size to it. But turns out that it can't be done. It's just simply too broad to talk about all subsets of the real. Because if we assume something called the axiom of choice, in set theory, AOC, if we take that, okay, if we assume that, if we're okay with that, then it is possible to construct something called a non-measurable set. And by that we mean, if we're allowed to assign sizes to non-measurable sets, then these three axioms became mutually contradictory, which is not good, right? We don't like that to happen. So a compromise must be taken. Either you drop one of these axioms, or we're going to restrict the class of subsets to which we're going to assign sizes to. Okay, so the second option is to give up the ambition of assigning measures to all subsets of real. And that is the choice that most mathematicians opt for. Because in analysis, typically you don't need to assign measures to all subsets. Okay. Instead, we're just going to choose to assign measures to sets that can be approximated by open sets. Okay, so that's the most famous class of subsets we're going to discuss. I mean, not going to discuss today, but in measure theoretic probability, the technical jargon is called the Barreal sigma algebra. Okay, I'm just dropping names like crazy now because it's a deep rabbit hole. Barreal sigma algebra. So the Barreal sigma algebra is a collection of subsets that can be approximated by open sets on the real line. And those are the sets are the ones we're going to assign measures to in measure theory. It seems like we could have irrational line segment. No, so line segment or intervals. Okay, so this notation means all the reals, x in real, such that x is between a and b. You cannot have a line segment full of irrationals because both rationals and irrationals are dense, so-called dense on the real line. Okay, you cannot pick a line segment that consists of only irrationals. Okay, because both rationals and irrationals are dense in real. Once again, this is topic in elementary analysis. Yeah. So so there's that. I mean, the real line turns out to be extremely intricate. I think I said something in my post about the complex analysis course is that the real line, the problem of continuum is a conundrum with just unthinkable intricacy. Okay, without such delicate issues, measure theory would be very straightforward. It's unfortunately not the case. The problem of the continuum is one that plagued mathematics for over 2 centuries. And however, if you assume that the real numbers are understood, then complex numbers are extremely easy. So complex numbers for beginners, for the uninitiated, feels unnatural, right? Because you introduce this minus 1 square root thing. It feels unnatural. But for people who have seen some real analysis, he would know real analysis is much harder than complex analysis. Once you assume the properties of the real numbers, the complex numbers are a piece of cake, and often theorem seems too good to be true. To the uninitiated, the real line is totally uninteresting. It's just a line of points. What else can be said? But no, this is a monstrous object. The real line is a monstrous object. Okay, and all sorts of weird counterexamples is lurking in the dark about this fascinating monster. Anyway, so I strayed too far because I was just briefly mentioning that distribution is a measure. The distribution is a measure, and here in probability theory, a huge topic is the convergence of measure, and there are different modes of convergence. And actually, in our stochastic calculus series, in episode 1, we introduced another mode of convergence called the convergence in the mean square sense. Okay, which is not here. You can go to the episode 1 of stochastic series to find out. Okay. Still, chapter 4 is technically speaking probability theory. But this is perhaps the most important chapter in probability theory for statistics. Okay, for statistics. So to do statistics, you cannot go very far without knowing sampling distributions and mode of convergence. Okay. And in most situations, sampling distributions are notoriously difficult to determine precisely. And that's why some sort of approximation is needed. Large sample approximation is one. A Monte Carlo approximation is another. Okay, so large sample approximation already include Monte Carlo approximation. It's just that in Monte Carlo approximation, you're even less relying on analytic formulas. I did my grad research in Monte Carlo simulations of stochastic processes. It's for MRI. It's for a specific technique of MRI called diffusion MRI. Okay, so still very active area of research. It is endlessly fascinating. Okay, so here we're still in probability theory, but perhaps the most important chapter in probability for statistics. Okay, I'm risking going on a side tangent again. Probability theory. Let's just put it this way: if you're studying probability for statistics, as I said, sampling distributions or limits are tremendously useful, foundationally important. And this is really a form of transformation of random variables. So in statistics, the kind of probability theory you see the most is the transformation of random variables or a sequence of random variables. You take a bunch of random variables, you apply a function to it, you get a new number, a new random variable, and you wish to discuss the distribution or some properties like the mean and variance of the new distribution. So I would say like 90% of statistics is just doing that. Of course, it's easy to state the problem. The actual analysis can be insanely complicated. That's one aspect of the probability theory, about transformation of random variables. And there's another aspect called conditioning. So conditioning is also another pillar of statistics. And even stronger pillar for stochastic processes, conditioning. I'm talking about conditional probability, conditional expectations, and so on. For example, to predict a random value, you usually use some sort of auxiliary information, right? So that is a form of conditioning. So given that it rained today, what is the probability of it's going to rain tomorrow? A simple example in real life. And conditional distributions, conditional probability, conditional expectation is the mathematical basis for Bayesian inference. Bayesian inference is all about conditional probabilities. Okay, and when you discuss things like time series analysis, and time series analysis, and what else? Like Kalman filtering. You guys might have heard of Kalman filtering in engineering. So this is the algorithm that won the space race, or at least that's the romantic way to put it. I mean, nobody actually won the space race, in my opinion, but it was certainly important for the space race, for filtering, for prediction. Kalman filters is extremely powerful and is still widely used today. Anyway, so in chapter 5, we're getting into the concepts in statistical inference. Hang on, what's going on? This is not the full document, okay? Right, it's not the full document. Chapter 5 discuss some of the fundamentals of statistical inference, or I would say is a more statistical inference for pedestrians. Statistical inference for pedestrians. So there's not much actual calculation going on, and it's just for conceptual understanding. So basically, in statistics, there are two major branches, roughly speaking. You have the descriptive statistics and statistical inference. Descriptive statistics is purely about the data set. So it is about come up with tools to visualize the main characteristics of the data set. Okay, and it's also about finding summary statistics for a particular data set. It's all about the data set itself. It sounds quite simple, right? But it can be a huge leap in research progress if you can get an interpretable set of characteristics for a large data set. And in practice, data set can have higher dimensional, so can be very high, can be high dimensional, like an image. Right? An image, a video, these are examples of high dimensional data sets. And what's typical for high dimensional data sets is that they are very difficult to visualize. Descriptive statistics develops these tools to summarize and visualize complicated data sets, so some sort of conclusion can be drawn just from the data set alone. But inferential statistics or statistical inference goes one step further. It is not only about the data set anymore. In statistical inference, we wish to say something about the underlying population, right? The underlying data generation mechanism that gives rise to the data set. So that's statistical inference. So you're making inference. You infer something, right? That's the operative word here. You don't just, you're not just saying, okay, this data set has an average of X. We're not only interested in that. We wish to say, okay, the population mean is most likely to be around what values. So that's what statistical inference is about. Because typically it is quite expensive to do a census, so-called census. I'm pretty sure everybody has completed a census in their home country at least once. Or like in econ variables like income or need their own dimension. Exactly. Yeah. Income, age, education. Right. So to describe a household, you have all these variables. Right. And if you have more than 3 axes, it's already impossible to displace them in the usual Euclidean space, right? You can define them, but it's hard to visualize them, right? So some sort of summary has to be created, right? So anyway, back to inference. We wish to say something about the underlying population or the underlying data generation mechanism based on the finite sample we collect from those population, because typically it is infeasible to do a census of the population. Typically that's not possible. Right? So that's why statistical inference exists. So it sounds like a pretty big subject, and it is. But to narrow things down a little bit, to make things more manageable, at elementary level, which is the level of this book, we typically discuss 3 problems in statistical inference. Point estimation. It's called point estimation. I'll give these names. Point estimations, interval estimation, and hypothesis testing. So for point estimation, we just wish to come up with one point or one number or one vector, depending on what you're estimating, of the unknown. Okay, so let's say you have an unknown average, unknown population mean. Right? A point estimate is just one number. Let's say, okay, it is estimated that the population mean is 10 in whatever unit. Just give one number. Okay, that's the theory of point estimation. Of course, you need to design procedures to get those estimates systematically, and you need to be able to evaluate your method. Okay, why this is a reasonable method? Okay? Why is your way to produce a point estimate a reasonable estimate? Okay? Why is this reasonable? Why is this estimate a reasonable one? Right. So you need some sort of principled scheme to develop these things. I'll say this: statistics is not mathematics. Mathematical statistics is a branch of probability theory, but statistics on its own is not mathematics. Statistics on its own is a very unusual science. Okay, it's not natural science. I mean, nowadays we like to call it part of data science, but um, it really is a branch of epistemology, which is a branch of philosophy. It is about how do human beings obtain knowledge. Epistemology. It is about what can be known and how do we obtain such knowledge. Like what can be known? That's one question, and how can we get to know things, right? So this is a branch of epistemology that dressed up in mathematical language. Okay, and what sort of mathematical language? Roots in formal logic. There are people who argue that probability is a branch of logic. I don't necessarily, I don't think I share that view. Okay, but it can certainly. There are people who argue that. Yeah, there are people who argue that statistics is the logic for uncertainty. Yeah, some sort of So there's certainly a camp of people who support that because the foundation of statistics is actually surprisingly murky. Okay, I mean, in mathematics we have now more or less a foundation that's supported by the majority of the community, the ZFC, right? The ZFC, basically that's an acronym for the fundamental axioms of set theory, on which the major branches of mathematics is built upon. In statistics, there is still not a commonly agreed upon foundation. Right? For epistemology, it relies on. Actually, I'm very, shall we say, not very well learned in philosophy. Okay, I'm interested in it, but I never taken a formal course in that. But basically, statistics, I don't think it's controversial to call that a branch of epistemology, dressed up in mathematical language. So what sort of mathematics? Well, we already mentioned probability theory, that's obvious. But because fundamentally speaking, statistical inference, as I said, it would not exist. There's no need for statistical inference if we can always do census, right? If we can always do census, then there's no need for statistical inference. Statistical inference exists, and it gives an uncanny formula. Exactly, because it is not a normal math. It is absolutely not normal math. It uses a lot of math. It looks like math, right? If you look at advanced statistics book, it has proposition, theorem, proofs, corollaries. That looks kind of like a math textbook. But fundamentally speaking, this is not a branch of math. Just like, I mean, you can think of mathematical physics as a branch of mathematics. You can certainly do so. And mathematical statistics is a branch of probability theory, which is math. But at its core, physics is not math, right? Of course, I think we can all agree that physics is not math. They have different objectives. Statistics is also a distinct subject with its own objectives. Okay, because fundamentally speaking, it is epistemology. It is about how human beings acquire knowledge and also what is knowledge. So there's that. I mean, yeah, I'm not going to go into the controversy of the set theory. That's too far away from what we're doing now. But I'm trying to say is statistics, okay? Statistics is a branch of epistemology dressed up in mathematical language, and statistical inference, being a subfield of statistics, has its own particular mathematical language. One is probability theory. That's obvious. Well, but in case it's still not obvious, let's put it this way. Because to make inference, you're essentially saying which estimate is more likely, right? Which estimate is more likely? Which estimate is more likely to be accurate? But to even discuss such things, you need to make probabilistic assumptions about the distribution. Okay, you can say the distribution, the underlying population is normally distributed. A very common assumption. So now you have to introduce probabilistic assumptions about the behavior of your errors, or the behavior of the underlying distribution, this is where probability theory enters statistics. You're making assumptions about the data generating mechanism of this data set. So that's one. And another major pillar of statistical inference is optimization. Okay, that might not seem very obvious. Why do you need optimization? Optimization is a branch of applied mathematics. Why do you need optimization for statistical inference? Well, that is because, as I mentioned, you cannot do census all the time. You only have finitely many data points. Okay, we can always do census, so you have to rely on finite samples. So you have a finite resources for investigation. So you want to extract the maximum possible knowledge defined in a precise way from the data set. We want to maximize knowledge. Economists maximizes utility and revenues. Okay, statisticians maximize knowledge about the underlying distribution from what's given, the data set. So this is why most of the estimation methods in statistics is at its very core in an optimization problem. So that's why optimization is so crucial for statistics, for machine learning, for artificial intelligence. Okay, in machine learning, we talk about training a model. What does that mean? Are you literally training, like training an athlete? Yeah, exactly. We're minimizing the distance from observation on the mean. Right? That's one way to get an estimate, minimizing the square distance. Right? That's the least square estimate. Or you can use some fancier distance, like L1 distance, L1 distance, or the max distance. That's also possible. So you're minimizing some sort of loss function. The technical term is called a loss function to gain an estimate. Bayesians has their own criteria. And we're going to discuss likelihood-based estimates. That is to maximize likelihood. So when it comes down to the actual mathematics of statistical inference, two things are needed. Two major branches of mathematics are needed. As I was talking about, probability theory and optimization. To crunch out the actual numbers, you need linear algebra. So that's why you get this. Somebody said you get this uncanny feeling when you study stats. It does not feel like normal math, right? Because it uses math for its own end. Okay, so yeah, hopefully that was an okay non-technical introduction to statistical inference. Okay, so why do we need statistics? You know, and yeah, I'm not going to read through them all, but because we want to get into the actual methods. But yeah, there's some very nice conceptual questions here. You need to define your variable in your problem, because one temptation for data analysts and scientists is to immediately jump to the model, because we like our models. Right? We math people, we like our models, sometimes even more than the real world, because in the model, you have total control. You have all these nice assumptions, and sometimes we want to hide from reality. I mean, to put it bluntly, by hide behind complex models. That's the temptation. But here in chapter 5 of the book, we're actually defining like the fundamental aspect. Okay, when you use statistics to study a problem, okay, you have to be very clear what is your population. Okay, what is your population? What is the variable of interest? What is your sample scheme? Right. So these are, so to say, these are the what's going on behind the scene of any sort of fancy models. So you can think of a fancy model as a chef that turns ingredients into dishes. But to get those ingredients in the first place, okay, are often those who get the ingredients in the first place are the unsung hero in the food industry. Right? So that's what I'm trying to say here. Okay, so this is a good chapter to come back to, even for veterans in data science, in my opinion, because sometimes we get so mesmerized by our models that we forgot about the fundamentals. Okay, and here there's some data visualization techniques as well, I believe. Data visualization technique like the box plot and whatever. I think it's worth going over the section on statistical model. What do we mean by statistical model? So why don't we just start here? Okay. Actual reading start here. In a statistical problem, we're faced with uncertainty of a different character than that arising in 5.2. What's 5.2? Sorry, what's 5.2? I just want to give an idea of what 5.2 is about. Probability? No, inference using a probability model. Okay, inference about probability model. So if you have a probability model, that means let's say you're assuming the lifetime of a machine follows an exponential distribution. And this exponential distribution is fully specified, by the way. Exponential 1. You can write down the density function. You can write down the density function of this distribution, and then you can calculate the mean and variance and whatnot, okay, to talk about like the numerical characteristics of this model. But in most circumstances, you don't know the exact parameter of the model, even though actually most of the time you don't even know the class of the distribution. So this is a human imposed assumption. Okay? We assume that the distribution of a lifetime is exponential. So you have a family of functions for the density. But the parameter is treated unknown. So that's a parametric statistical model. Actually, let's go to the 5.3. We know what 5.2 is about. So you're making you're setting up a probability distribution that is fully specified. That's a probability model. Okay. In a statistical context, we observe the data S, but we are uncertain about P. Okay. P stands for population, by the way. You observe a data, but you're uncertain about the population. Okay. For example, you just have one machine, and you know its lifetime. Okay. Say if you bought a Roomba, and it lasted for 10 years. Okay. But you wanted to know how do most of the Roombas last. Right. So in this situation, we want to construct inferences about P based on S. How we should go about making these statistical inferences is probably not at all obvious. Absolutely. It's not obvious at all. Okay. So that's why statistics is so controversial. Even like different in mathematics, okay, in pure applied mathematics, you have at least you have a commonly agreed problem, and people have different research directions, like the Hilbert problems, probably the most famous ones. Okay, so at least in those areas, in mathematics, people tend to agree what the problem is. In statistics, sometimes people don't even agree how the problem should be formulated. So even though two people are claiming to be solving the same problem, they're actually not. So what makes statistics interesting, but also difficult to learn. In fact, there are several possible approaches that we will discuss in subsequent chapters. Okay, so at an elementary level, perhaps the most schism is frequentist versus Bayesian. Okay, so there was a time in the history of statistics where the two schools were extremely hostile towards each other. The likelihood-based, frequentist statisticians and Bayesians were extremely hostile towards each other. Needless to say, that wasn't very healthy, right, for the subject, even though there are genuine disagreements. And also there are some personal dramas as well. But nowadays, that's when you disagree with how problem is formulated. You're very welcome to do so. So a little bit about my background. My university, the stat department of my university, was very heavily dominated by frequentists or likelihood school. We don't even have a separate course on Bayesian inference. It is only usually a chapter in a bigger course, and that's about it. And the other chapters of the course are all frequentist based. So that's my background. So I tend to think in terms of frequentist inference, even though I'm familiar with the fundamentals of Bayesian. Okay, and at University of Toronto, however, they do have separate courses. Hopefully, I think multiple, at least one. Okay, at least one separate courses are separate course at the undergraduate level on Bayesian statistics. Okay, but nowadays Bayesian is not only part of the mainstream, but it also, even though it's still not as dominant as the frequentist school, but is accepted within the mainstream, and now even trendy to be a self-described Bayesian. Okay, so yeah, that's the status of Bayesian statistics. But anyway, I think regardless, you can only appreciate Bayesianism. You can only appreciate Bayesianism if you have a foundation in likelihood or frequentist statistics. Okay, so that's the thing. Because if you're a Bayesian, okay, if you're going to be a Bayesian, and you're very welcome to do so, you want to show the superiority of that methodology, right? And who is the biggest competitor? Of course, frequentists. Right? So you usually that's how much of the debates are conducted in the stats community. Right? So anyway, you can. I'm trying to say is doesn't matter what sort of school you choose to subscribe at the end, or even start your own school. These fundamentals are at least common. Okay. So in this chapter, we develop the basic ingredients of all the approaches. That's cool. Common to virtually all approaches to statistical inference is the concept of the statistical model. Okay, statistical model, that's a technical term for the data S. This takes the form of a set P with a subscript theta. Theta belongs to big omega, our probability measures, one of which corresponds to the true unknown probability measure P that produces the data S. Okay, so this deserves some sort of explanation. I apologize that these notes are a little bit chaotic, okay? I don't know if I should upload these. But just imagine a simple situation. Okay. Maybe let's just flip coins. Okay, let's just flip coins. So now imagine you're flipping coins. And these coins has the probability of getting a head that is equal to P, and probability of getting a tail is of course 1 minus P, which we denote as Q. Right. So what's the probability model here? Flipping, let's say, just one coin. Just flip just one coin, or no coins. To make it as simple as possible, just flip one coin. Then the probability distribution is the Bernoulli distribution. literally the Bernoulli distribution. If X follows the Bernoulli distribution, then its distribution looks like this. X equals 0 has a probability of Q, and X equals 1 has a probability of P. This is a probability of X equals K. And here this is, the first row is K, okay? Okay, so it's just a little table here. And P ranges from 0 to 1, open interval. If you allow closed interval, then the distribution becomes degenerate. Okay, so let's just say the distribution is non-degenerate. P is strictly greater than 0 and less than 1. Then you have a probability measure, a family of probability measure indexed by the parameter P, Bernoulli P. Okay, so that's an example of a statistical model. It fits the definition. Okay, so now let's say you flip that coin, you get a head. You now have the data. Well, what can you say about P? What can you say about the true probability measure? What can you say about the true probability of getting a head? AKA, what is the true Bernoulli distribution? Right? So in other words, we are asserting that there is a random mechanism that generates S. And we know the corresponding probability measure is one of the probability measures in that family. Right? We know in the coin tossing example that the true probability measure is a Bernoulli distribution. It's a unique probability distribution. That's something that we assume. It kind of makes sense, right? It kind of we like to think that the true probability of getting a head is a fixed number, which corresponds to a unique Bernoulli distribution. Right? So the statistical model P theta labeled by theta corresponds to the information a statistician brings to the application about what the true probability measure is, or at least what one is willing to assume about it. Right? So I think probably more about what one is willing to assume about it. Right? So often we make compromises with realism, between realism and trackability. Right? So depending on what sort of accuracy you want from your analysis, okay, sometimes you just want to have a qualitative picture, and that's totally okay. Just want to have a qualitative picture, enough to describe a difference, so to say. You don't need a super accurate prediction model, but you just want to confirm the presence of a certain effect. Right? Then, in those situations, you can choose your statistical model to be more analytically trackable. It's just a fancy word of saying easier to do algebra and perhaps calculus with. But sometimes you want more realism. Sometimes you want more realism. So you want higher accuracy. So you tend to, but not always, okay, tend to choose a more complex model. So there's a trade-off usually between those two. So the statistical model is more about, in my opinion and experience, that is more about what one is willing to assume about a real-world situation. Okay, the variable theta is the parameter of the model. It's just for bookkeeping. The parameter of the model is like a label that distinguishes the members of the distribution in that model, because a model is a family of probability measures, right? It's a family of distribution. So theta is just for bookkeeping purposes to distinguish one member from another. And big omega is called the parameter space. So that's the collection of all possible parameters. In the coin tossing example, that's just the interval from 0 to 1. Typically, we use models where theta is in big omega indexes the probability measure in the model, as I said, i.e., p theta 1 equals p theta 2 if and only if theta 1 equals theta 2. Okay, so yeah, the two distributed high accuracy can be a problem. Infinite degree polynomial will go through all the data but won't predict the next data. Exactly. If something that overfits your data set, right? If something that overfit your data set, then it can be a disaster for unseen observations. That's certainly true, right? So, I mean, usually when we say high accuracy, we mean an accuracy that is good enough for both the training and testing data set. Otherwise, on, only high accuracy on the training data set is kind of useless, right? So that's the thing I'm trying to say is if you want to achieve high degree of accuracy, typically you make some compromise in terms of interpretability and analytic trackability. Okay. Anyway, if the probability measures p theta can be all presented via probability functions or density functions, so here comes the probability assumptions, right? Probability functions means a cumulative distribution function. A distribution function, okay, the probability function here, okay, let me just write it here. Okay, probability function. Probability function is sometimes called CDF, or cumulative distribution function. Probability function of a random variable x is defined as follows. Okay, so this is a function in little x. This is a function in little x. And it is always monotone increasing. It's always monotone increasing. So that is to say, if x is less than y, then big F of little x is less than or equal to big F of little y. Let's think about why. Let's think about why this is the case, even though it's quite basic probability theory. Well, if big X is less than or equal to little x, and x is less than y, then simply by the transitivity of inequality, big X is less than or equal to little y. That is to say, i.e., when x is less than y, okay, when x is less than y, what? Then the event big X less than or equal to little x is a subset. Okay, here we perhaps need to make some explanation of what this means. What does this mean? Well, let me just type instead of writing. Okay. Notations. So remember, a random variable is a function. A random variable x is a function. Is a function. Usually we use big omega as sample space, but unfortunately here in the textbook, big omega stands for the parameter space. So let me use a different letter. X, say, let's just say from scripted x, okay, to R. So you can think of in terms of the coin tossing example. So x is the collection of outcomes, head or tail. And you can map that to real numbers. Let's say head is 1 and tail is 0. So this way, the coin toss experiment is now encoded by this random variable, which is a function. It is a function, right? So when we say something like this, big little x, big x less than or equal to little x, the notation notation, big X less than or equal to little x is really a shorthand of the set of little omega in the sample space such that big X of little omega is less than or equal to little x. All right? Because probabilists, they like to suppress the argument in a function. Probabilists like to suppress the argument in a function, the reason for which is beyond the scope of this discussion. Okay? Because probabilists like to write things like bigger X less than or equal to little x. Okay? And not just for brevity. Okay. It means that we're looking at the inverse image. Okay, by the way, this is equivalent to the inverse image. Have you guys seen this notation before? X inverse of the set minus infinity to x. Okay, have you guys seen this notation before? These two are equivalent. This is the inverse image of the interval minus infinity to little x under the function big X. Okay, when we write x inverse, we don't assume the function is invertible. This is a complete notation. This means the inverse image of a set. This consists of the element little omega in big X such that x of omega is less than or equal to x. So this is what it says. And so when we write this, what we're really making a statement is that one subset or one event is contained in another. Okay, so here it should be clear why big X less than or little x is a subset of big X less than or equal to y, because we're talking about the collection of little omega in the set of the left-hand side. On the left-hand side, we're talking about the collection of little omega such that x of omega is less than or equal to x. But because x is less than or equal to y, is less than y. Big X is less than y. Little x is less than y. Sorry, little x is less than y. That means whatever omega in the set on the left-hand side is an element of the set on the right-hand side, which is exactly the meaning of set containment. And it is an axiom in probability that if you have two sets that are nested, okay, A contains B, then PA must be greater or equal to PB. Intuitive, right? Because, as I said, probability is a measure. It behaves kind of like area. If one set contains another, then the bigger set must have a bigger measure. Okay, so here, therefore, P big X less than or equal to little x is less than or equal to P of big X less than or equal to y, which is exactly the same as big F of x is less than big F of y. Sorry, inventive. You said no, I have not. You mean the inverse image notation, right? Okay, definition. So this is more a you're most likely to see it in the introduction to proof course, the notation of inverse image. Okay, let's just consider let A and B be set. Okay, so these are like the language of proof-based mathematics. Let A and B be set. Let f be a function from A to B. Okay, so these are sets. They don't have to be set of numbers. Okay, they can be set of anything. Set of people, set of cars. Who cares? And f is just a mapping from A to B. Okay, It's a function that, let's say a is the set of integers, b is the set of reals. So f is a function that assigns each number, each integer, a real number. Okay, it's just a simple example. So here you have a function f, and we can define the let's define two things. Okay, first we define the image. Define, okay, one, the image of a subset, say C of A under F. So what does that mean? Well, it means first of all, we have a notation, f of C. We write f of C. We write a f of C, and here it is. I'm going about this to explain the notation of image and inverse image. Okay, inventive. I presume this is something that you when you said no, I have not. I presume this is something you have never seen. Okay, so let me clarify. F of C is f of C is little b is a collection of little b in big B. Is a collection of little b in big B such that f of b equals f of little c for some c in big C. Okay. Let me draw the picture. Okay, I choose, by the way, a minor note. I changed the background color. I changed the background color to this color. I don't know how do I describe it, because somebody and a few people actually complained, I mean in a good way, in the comments on my last video, that they say that the white color is too blinding. Okay, it hurts their eyes. So I changed this to this more like I don't even know what's the color, but I kind of like it. It's kind of a more pleasant color. They actually requested a dark mode. I mean, the channel initially started from a dark mode, but I became to dislike that. So I don't want to do a dark mode. Perhaps this is a reasonable compromise. Anyway, so here's the diagram. Here you have a set A and a set B. And there's a function that maps from A to B. So that's the schematic here. So let's say this is a subset, C of A. Then FC is what? F of C right here is this part. So basically everything in F of C, this notation F big of C, everything in here is the function value of something in big C. Looks nice, like the color. Okay, cool. Awesome. I'll use this color for all my future slides. Okay, so that's the diagram for the image. So what's the pre-image? Well, the pre-image is the opposite direction. Let's define the pre-image or the inverse image. The inverse image of a or pre-image, aka pre-image of a subset D of a subset D of B. Okay, under F, still under F. Okay. What does this mean? Well, for that we have a notation F inverse of D. F inverse of D. By the way, this is a full notation. You cannot separate them in terms of, okay, f inverse. Okay, I'm not saying f inverse exists. F may not be an invertible function, but still, this notation as a whole still makes sense, which is what we're defining right now. Okay, f inverse of D is the collection of little a in big A such that f of A belongs to D. Okay, and by the way, let me just put that here. Okay, a good source for this sort of notation is a book called How to Prove It. This is like an introduction to proof-based mathematics. How to prove it. This one, how to prove it. Okay, so it introduces the language of set theory, the logic, prepositional logic, the notation of logic, and some elementary number theory to practice such notations. Okay, typically, if you're a math major, you take that kind of course in your first year. The course title goes something along the line of Introduction to Mathematical Reasoning. Okay, basically, an introduction to proof writing. That's it. But as I declared on the channel, I don't assume all my audience has a background in proof writing, because typically in North America, at least, only math majors takes proof writing courses, and this is an applied mathematics channel. It's not just for math majors, it's also for people who are interested in using math as a tool, right? But unfortunately, unfortunately, in a pedagogical way, not unfortunately in a scientific way, is that pretty much all higher mathematics requires some literacy when it comes to proofreading and writing, and especially like fundamental notations like the pre-image or inverse image is, I guess, not always emphasized in more computational courses, okay, of higher mathematics like calculus. But this is definitely very common. We need to, everyone who wants to self-study mathematics needs to know these symbols. Okay, because these are like the fundamental language of proof writing, a proof-based mathematics. Okay, so now let's introduce another diagram to illustrate the pre-image. All right, so there you go. You still have the domain and codomain, A and B, and the same function. Okay, and I would like to mention something. In general, the codomain does not have to be the range. In general, the set B only needs to include all the possible outcomes of f, or the possible outputs of f. It does not have to be only the possible output of f, if that makes sense. So let's just say, in the domain, every point is a valid input. Okay, f must be able to take everything in A as an input. I guess I just get confused with why the inverse function would be in the notation. I do get what the inverse function is. Actually, here, okay, actually, let me finish drawing this picture of why the minus infinity is here. Okay, it's actually quite straightforward. So the inverse image is defined as follows. So imagine this is A, and this is the range of A. This is the range of A, or should we say the image of A? Why don't we just use what we've already learned? This is f of A. So everything in A gets mapped to this little part of B. As I mentioned, the set B only needs to contain all the possible outputs of f. It does not need to be all the possible outputs of f. It can have more stuff. Okay, for example, you can write f from R to R. F of x equals x squared. But of course, we know that the outputs are always non-negative. It does not take all the possible values in R, but this is still a valid, perfectly valid function. Okay, so let's just say f of a is only a part of b, like what is shown here. Okay, and now we're picking a subset D of B. So let's say this is D. Okay, maybe I should use a different color. So this is D. So this is D. And now we're looking for elements in big A such that f of that element falls into D. But we know, you see, in general, D is not a subset of the range FA. Not necessarily so. They may not even they may not even overlap at all. Okay, but this is a typical situation. It has some part that overlaps with the range and certain parts that don't. But regardless, the definition for the preimage is the same. It is just a collection of little a in big A such that FA gets mapped to the set D. Okay, the only part in D that will take values in F is this little highlighted part. Hello, hi Vernon. Vernon Kuhn. Hi. So F inverse D is this set. Little a is here. If little a is inside, then f of little a gets mapped here. So this is the inverse image. Okay, this is the inverse image. So basically, if we go back to the notation for the event, big X less than or equal to little x. Okay, because in probability theory we write this a lot. This is an event big X random variable less than or equal to a value, say x. As I mentioned, this is a shorthand for the collection of outcomes, omega, in the sample space, scripted x. Scripted x, okay? The collection of outcomes. So when you think of collection of outcomes, you think of heads and tails of tossing a coin, okay? And the values of random variables are numbers, real numbers. X of little omega less than or equal to big X. Well, what is that? Well, this is the same as writing x of omega belongs to the interval minus infinity to x, like this, right? This is the same. The inequality is the same as the set notation. And check this out. The definition of inverse image. The set of little omega in big X such that the function value x of omega is in the set minus infinity to x. Minus infinity to x is a subset of real. So isn't that just the same of x inverse minus infinity to little x, right? So inventive, did you understand? Did you get why this notation comes from? Right. So it follows from the definition of inverse image. Okay. So that's the. So this is what we're saying here. So all of this is for discussing this property of the probability function, or aka cumulative distribution function, which is an increasing function. Okay, and by the way, in the probability function or cumulative distribution function, little x can take any real value. Okay, this is always the case. Actually, you know what? You guys give me 1 minute. I want to get some water. I'll be back in 1 minute. the direction of one-dimensional vector. Well, this is not a vector. Okay, this is not a vector. It's just to indicate that the image maps the image of a set C. Okay, and to visualize the procedure of mapping C to FC. This is not a literal vector. Okay, this is not a literal vector. This is just for visualizing the process of mapping the set C, which is a subset of A, to f of C. F of C is the image. Okay, we take this as the definition as the image f of C. Okay. The inverse image, the inverse image f of inverse D, well, that takes a subset D, which is in the codomain, and pull it back to the domain. Okay, hopefully that makes sense. This is a notation. F inverse of D is the notation for this set. We're looking for values. We're looking for values of input in the domain such that its output falls in D. Make sense? It's kind of, let's just think about a more concrete example, okay? Where because in politics we talk about things like the 1%. What's the 1% in popular discourse? Especially if you follow left-wing politics. What is the 1%? The 1% refers to the population who owns who owns the what like the, I don't know, like how many percent of the national wealth, right? So the domain here is the set of population, the set of people. On the right, you have wealth. Each person has a certain amount of wealth. Right? Each person has a certain amount of wealth. So let's say if your income sits at the 1%, like the top 1% of the wealth distribution, then that's what 1% means in politics. Right? So that's the inverse image in action. You're choosing a specific subset, right, on the real line, which models the wealth, right, which models the wealth, and let's say what's the cutoff point? I mean, let's say 1 million. If you own, if you have more than $1 million cash in your bank account, you're probably 1%, right? So that's the example of an inverse image. We're looking for, so back to the definition, we're looking for the collection of input A such that f of A falls into a specific subset that we specified in the codomain. Okay? So going back to this notation for the event big X less than or equal to little x is a shorthand of the collection of outcomes, little omega, in big X, such that x of omega less than or equal to little x. Okay, and this is just a conversion from the inequality to the set theory notation. And now this notation fits the definition of the inverse image. Okay, so in case this is still too complicated, we can map the people to wealth, and inversely we can map the wealth to people. We're not going to get a negative number of people. I'm confused. No, of course you're not going. This is okay. Okay, let me do an example. Okay. But forget about politics. Okay, it's too controversial anyway. Let's look at big X. Toss 3 coins. Okay, toss 3 coins just to make things a little bit non-trivial. Toss 3 coins. Toss 3 coins. Yeah. So what's the collection of outcomes here? Well, X is, you have head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, and tail, tail, tail. Make sense? So this is your big X. And let's define, this is big scripted X. So let's define the random variable, say X, unscripted X. X is X of omega. X is a random variable. X is a random variable that counts the number of heads in each outcome. Okay, so that's big X. So big X, as I said, is a random variable. Therefore, it is a set. This is a function that maps from scripted X to real. No. And well, and we can easily write down all the function values. It's gonna be a little bit tedious, but let's do the exercise regardless. X of 3 heads is, well, is 3. It counts the number of heads, no? Okay, and X of head, tail is what? Is 2. X of head, tail, head is 2. X of head, tail, tail is 1. X of tail, head is 2. X of tail, head, tail is 1. It counts the number of head. X of tail, head is 1, and X of tail, tail is 0. So is that clear? This function, it maps every outcome to a real number. You see, it does not take, it cannot take every possible real number. That's not possible because there are only total 8 outcomes in, there are only 8 outcomes in total. The range of the function does not have to be the codomain, which is illustrated here, right? So that's the function. This is completely defined, right? All the inputs is and the corresponding outputs are given here. So when we say what is the event? The event, okay, the event, let's say X is less than or equal to 2 means what? Well, this is the event, X less than or equal to 2. An event is a set, so we write this. We put a curly bracket around it to indicate this is the event. How did I define it? Well, this is the collection of little omega in big omega, not in big omega, in scripted X, such that X of little omega is less than or equal to 2. Right? And of course, this is the same as little omega in big X, scripted X, such that X of omega is in the interval minus infinity, because this is really just, converting the inequality into set notation, no? That's it. Even though it cannot take negative numbers, we don't care. X less than or equal to 2 is the same as X of omega belongs to the closed interval, the closed interval minus infinity to 2. Yeah, so that's it. And we can write it as the inverse image notation, X inverse of minus infinity to 2. Okay, so which of these inputs, right? So there are 8 inputs in total for big X. There are 8 inputs in total for big X. Which of these has an X value that falls in the interval minus infinity to 2? Does the first one work? No, it doesn't. Right? The first input HHH has a value of 3. It is not. X of omega is not in the minus 2 to minus infinity to 2, so HHH is not included. The second one is included, because its function value is in the set minus infinity to 2. And in fact, everything else except the first one is in it. So this turns out to be, the set turns out to be everything except HHH. We can write it this way, or the set difference notation. Scripted x, scripted big X, set minus HHH, which is completely and utterly trivial, okay? Because you can just tell that from the very beginning. It's a random variable that counts the number of heads in each outcome. It's x less than or equal to 2 means number of heads is less than or equal to 2, which of course you cannot include the head, everything else counts, right? So this is just a formal way to encode all of those verbal description. Right? So of course, intuitively speaking, if x is a random variable that counts the number of heads in each outcome, the event x less than or equal to 2 consists of all the possible outcomes except the first one. That's completely obvious, right? But what we're doing here is to practice this notation. Inventive? Is that better? Is that better? Because I'm using this rather trivial example to illustrate how this notation works. Okay. The random variable is a function. An event is a subset of the sample space. And we often talk about one specific kind of event, a random variable less than or equal to a value. So basically a random variable is in an interval. Here the random variable x falls in the interval minus infinity to 2. First time seeing a way to type formatted notation in real time. Interesting. So yeah, I mean, this is a Word equation editor. It is not super powerful like a proper LaTeX, okay? But it gets most of the stuff done. Actually, most of my slides for the videos are uses the Word equation editor or PowerPoint equation editor. Okay. Yeah, okay, got it. If we were doing, it would be different. Exactly. Right? So, more example. If x is greater than 2, what does this event mean? So, can we skip the intermediate step and jump straight to the last notation? This is equivalent to x inverse. So, what does greater than 2 mean? So, how do you write greater than 2 in a set notation? If something is greater than 2, it belongs to the interval 2 to infinity, open interval. So this is the inverse image of 2 to infinity. Right? That's it. Okay, so now you just look, okay, which of these outcomes? By an outcome, I mean one of those 8 things, okay? You see, well, in mathematics, not everything has to be numbers. But still, we like to work with numbers. Right? So a random variable is converting an outcome, converts an outcome to a number. So you can, well, apply mathematics to it. Right? That's the simple motivation. And a random variable is a measurement of an outcome. Exactly. So it's just HHH. Totally correct. And this is once again completely obvious because x greater than 2, it just means the event that has strictly greater than 2 heads. Well, you only toss 3 coins. That means 3 heads. Again, totally obvious, but you can work it out using the abstract notation. It's hard to take the inverse of an element. Well, the inverse of an element, what you're saying is, well, if you have a function that maps a set into a set of mammals, so to say. Okay, so going back to the original diagram, A is some unknown set, okay, which, I mean, the details we don't care about. Let's say B is a set of mammals. Elephant is a mammal, then it makes sense to say F inverse of elephant. That's a well-defined notion. It's hard to take. It's hard because you have not specified what A and F are. If you have specified them, then it's not hard, or at least in principle. Okay. Yeah. So that's the notation of set theory. Okay. Actually, you know what? Can we maybe go back? Hopefully YouTube don't destroy my channel because I showed this part of the book. Okay, I'm risking the future of the channel for this little. I'm okay. This little part. So basically here you can see functions. So what I just showed here, image and pre-image and all of that, is chapter 5. So usually what you do in a proofreading course, you start from logic and some proof strategies, because proof is based on every proof, okay, no exception. Every proof is based on the logical structure of the statement. So you start with logic first, and then you start from basic strategies for formulating to search for a proof. Okay, and then you discuss sets in details. Okay, so relation is a type of set. Yeah, relation is a type of set. You heard that. Relation is a type of set. So it's a relation is. I mean, I don't want to get into this for no reason, but basically, this is set theory. Surely you can find other legal sources for that. Yeah. I don't know actually. It's not like, I mean, I've read tons of books, like, well, I actually yeah, that's why we need the the Google Doc for book recommendation that are free and safe to live stream. Okay, I'm gonna close this now. I'm just pointing out resources. Okay, so this is an extremely representative course on proofreading, the basic language of abstract mathematics. Okay. Anyway. All right. Okay. So where were we? Okay. We're talking about probability measures, probability distributions, and whatnot. So this is a very important foundation because we want to be clear about what we mean by those functions. Okay. So our density function, the density function f of theta is the derivative of the probability function, aka CDF, assuming that the CDF is differentiable, of course. Okay. So in elementary probability, you only discuss two kinds of distribution, discrete and continuous. Even though that's not strictly very accurate terminology, it is good enough in practice. Okay, discrete and continuous distribution. So for continuous distribution, you can talk about densities. Once again, not a very mathematically precise statement, but we can get away with it at this level. Okay, I know some of my viewers are very advanced based on the questions they ask in the comment section, and I'm very flattered I'm able to attract such an elite group of audience. It's quite amazing. But anyway, I'm just trying to put out these disclaimers before I get destroyed again in the comment section. The walls of Ivory Tower Academia. You mean the paywall? Yeah, for sure. For sure. This is how it is, right? But it's not all depressing and all that, because there's still, as Vernon mentioned, surely you can find other legal sources. It's just I don't know. That's the problem. Perhaps I should AI it. Okay, recommend me a free resource on proof writing. Okay. I only know how to prove it, and another book which is not free, but I quite like it. Hang on, let me find that. is another book which I quite recommend. It's called The Tools of Mathematical Reasoning. I think I recommended in one of my videos, one of my old videos. So this book, The Tools of Mathematical Reasoning, it's not very thick, but for a, you know, it's only 270 pages, but for some reason it's 121 Canadian dollars. I mean, these publishers, man, I have no words. This is a good book, though. Still, we don't want to judge the quality of a book based on the ridiculous price it charges. This is still a very good book, and I think it is more. It covers actually a little bit more than How to Prove It. Okay, because in How to Prove It, you're only sort of given the tools, like the grammars of mathematics, which, I mean, of course, important, but still, you might not see why this is interesting. Here in this book, you will do some non-trivial applications such as elementary number theory. Here you can do some elementary number theory and as well as some basic real analysis to see the payoff of training in proof writing. So there's that. This is also a book that I recommend. And the proofs in this book are extremely approachable. And actually it spells out the, so to say, the process of looking for a proof. But I will warn that this book does not have solution manuals. The author, Tamara J. Lakins, specifically mentioned in the preface that, she said you should be able to mimic or at least learn the structure of proofs from the examples. Okay, and she thinks if you just put out a solution manual for proofs, then it's like the training data and testing data dilemma in machine learning, right? You don't want everything to be purely training data. By training data, we mean a problem and its solution. For testing data, you only have the problem, but you don't have the solution. So this way, you can fit the model, but you don't overfit. All right. This book is more demanding, in my opinion, than How to Prove It. But still, it's a very good book, and it's not like ridiculous as something like if you never have any proof background and you start to read Baby Rudin. It's not that It's not that. Okay. This is still very approachable. Okay. Anyway, let's come back to the stat inference here. It's common to write the statistical model as f of f little theta, f subscript theta, such as theta in omega. So this is what a statistical model is. It's a collection of distributions, and the distributions may be specified by CDFs or PDFs. If it's a discrete distribution like the coin toss example, you would use something called the probability mass function instead of density function. But anyway, what little f means is clear from the context. From the definition of a statistical model, we see that there is a unique little theta in big omega such that p theta is the true probability measure. Yeah, that's the previous paragraph. We refer to this value as the true parameter value. Okay, so let's say in a coin toss scenario, let's say the ground truth is that the coin is fair. Okay, 50-50 for heads and tail respectively. So in that case, the parameter for the Bernoulli distribution is 0.5. Okay, it is obviously equivalent to talk about making inferences about the true parameter value rather than the true probability measure, because you have this one-to-one correspondence between parameters and probability measures, right? So this is what we assumed. Two distributions are equal if and only if the two parameters, the bookkeeping indices, are the same. So you can because you can distinguish probability measures by their parameters, so you can just say we're making inferences about the parameter. Okay, I'm just wanting to say that theta here doesn't have to be a number. Okay, theta can be an arbitrary parameter. It can be a vector. It can be a function itself. Okay, so what we're about to see in subsequent chapters, theta is most often a number. But in general, theta doesn't have to be a number. Theta can be something even not a function. It can be, let's say, it can be a theory. It can be a theory. Okay, so what do you mean by that? Well, I'm going to invoke a example from physics. Okay, I'm going to invoke open should be sufficient for introductory math. Okay, we'll take a look at that. Okay, Vermont. We'll see if we can find a proof writing book that I like in the LibreText project, open textbook library. All right, so I was saying that I wanted to break the common misconception that a parameter is a number. It doesn't have to be. Okay, let's say you can think of the spectrum. You guys heard of the spectrum in physics? Wriggle, if you're in the chat, help me out if I make any mistakes. Sorry, okay? Because I'm not a physicist. What I'm saying is, in classical physics, the spectrum for light is a continuum. So you have a continuous distribution for the spectrum for the spectrum of light. Okay, so think of the color of light as a small part of the spectrum of light. Much of the light aren't visible, but in the classical theory, spectrum of light is a continuum. So you have a continuous distribution. Right? But in quantum theory, the spectrum of light is discrete. So you have a discrete distribution in quantum theory. So you can call theta 1 classical physics, theta 2 quantum physics. Okay, so imagine you observe a set of sample points from a spectrum. You wanted to determine, okay, is this described by classical physics or quantum physics? You don't know much physics. Okay, so perhaps that was a too complicated example. My apologies. Or let's say, so, okay, and so you and your partner, your boyfriend or girlfriend, you guys have your own food preferences. Okay? So let's say if I like Chinese food and I like Italian food and I like American food, right? This is like my taste. And my partner likes Japanese food, Korean food, and Thai food. Okay? So here the distribution describes the food taste. So it's like I'm 80% of the time I order Chinese food, 10% of the time I order Italian food. Should I do exterior calculus after vector calculus? Okay, because it's a little bit, yeah. And we'll come back to the Milky's question. So this is way off topic, but it's a good question. So I was saying that, the parameter can be quite general. Parameter here can be any element of an arbitrary set. I was just giving an example. Theta can be people. Theta 1 is Ming. Theta 2 is Ming's partner. And Ming's food taste is like 80% of the time he orders Chinese food, 10% of the time he orders Italian, and another 10% of the time he orders American. Okay, and Ming's partner has a different taste. Okay, Ming's partner theta 2 has a different distribution of food ordering. So she 30% of the time orders Japanese food, 40% of the time order Thai food, and what else? Another 30% of the time orders Korean food. Okay, so there are two different probability distributions labeled by people. Okay. Oh, hi, Nadia. Um, I mean, we go over things at a pretty leisurely pace. Okay, this is not like an intense lecture. Off topic, we're trying to show if is finite, then so is ex. Okay, so there we're getting a lot of questions in the chat, which is good. Any vector calculus book recommendation? My goodness, we're getting off way off topic. Okay, so why don't we take a little bit break from statistical inference so I can answer some of these questions. So someone asked for a vector calculus book, depending on what you want, right? Are you studying vector calculus for physics? Omega is a set of outcomes. No. Omega. I don't like this notation at all. This omega here is the set of parameters. Big omega is the parameter space. I don't know why they use that. Typically, okay, the canonical notation for parameter space is the Greek letter big theta. So it looks like a helicopter pad. Okay, this is the typical notation for parameter space. This is what you do. Little omega is the outcomes. Okay, so I use scripted x because here in the book it uses big omega for this for the parameter space. I don't know why. Okay, yeah, omega is a parameter space, so that's why. But typically in most texts, okay, in most texts you use the capital theta for the parameter space. Okay. Anyway, so it seems like a few folks are interested in vector calculus and its recommendation. So what I can recommend, once again, it depends on your objective, right? So who's the guy who asked the question? Who asked the vector calculus book? Haj, right? There's a classic called, I think it's called DivGrad and curl and all that. So this is like a first introduction to vector calculus because divergence, gradient, curl are the fundamental. These are the fundamental operators in vector calculus, and it's pretty physical. Okay, it's so this book can get you through most of the physics text that because vector calculus still dominates much of the physics text. Man, you can read Landau and Lifshitz. Have you guys heard of Landau and Lifshitz? This is some very intense physics book, and they still use the classic vector calculus stuff. Landau and Lifshitz. Yeah, Landau and Lifshitz, Course of Theoretical Physics, by at least two Russian physicists. They use the math there, the vector calculus there, are included here. Divgrad and Kern, all that is completely sufficient for reading the vector calculus in Landau and Lifshitz. So that's pretty cool. But if you want something more rigorous, because somebody also asked, if you should I do exterior calculus after vector calc? Right. Once again, depend on what you want. Let's say you want to study things like general relativity or classical mechanics or electrodynamics in an abstract way. So basically, Milky, if you're interested in theoretical physics, go for it. Totally worth it. If you want to do theoretical physics, you should totally do exterior calculus after vector calculus, 100%. Okay? But let's say if you want to do more applied physics, like fluid mechanics, then I don't think you would need that much. Okay. If you want to do theoretical classical mechanics, do relativity, quantum field theory, you should totally study exterior calculus and differential forms, So that's my recommendation. And for a good text on that, actually I have three to recommend. like rigorous vector calculus on steroid, on steroid. The first one is Calculus on Manifold by Spivak. This little book here, Calculus on Manifold. This little book. It's even got its own Wikipedia page, so it's very famous. So it's little, yeah, it is 158 pages. It's not very long, and it's extremely rigorous, but perhaps a little bit too terse. Okay, so this is like a standard reference on exterior calculus, meant as a first introduction to exterior calculus for advanced beginners. And the prerequisite for advanced for calculus on manifold is a course on elementary analysis. Okay, is a rigorous course on first single variable calculus is enough, or the first few chapters, like the first, I think 5 chapters in Baby Rudin is fine to read this book. And we also have another book which I also enjoy a lot, called Analysis on Manifold. One is called Calculus on Manifold, is Analysis on Manifold, but their content are largely overlapping. Analysis on Manifold by Moncrief, famous topologist. And this book has more details, okay? It's more intermediate steps than Spivak. Because you see, it's got 380 pages, and the content are very much the same. Okay, the Analysis on Manifold by Moncrief goes through things at a slower pace. Oh, this guy actually mathematical adventure. So this guy does tons of book reviews. Actually, put these two together: Calculus on Manifold on the left and Analysis on Manifold on the right. So they're a good combo. And I think there's even a better one. I mean, not better, but I hate to order these things because it's very difficult. But another work worth checking out is this one called Functions of Several Variables by Fleming. This is also a rigorous vector calculus, multivariable calculus text, and it's pretty well balanced in the sense that it has applications in mind. Okay, Fleming, this person, well, he does work in pure and applied math, so I think his book reflects his own working philosophy as well. So this is also a good one. It has concrete applications, or not concrete calculations. Okay, not much applications because the applications of this stuff is quite advanced. You need separate treaties, but still, applications are at least mentioned here. Whereas Spivak or Moncrief are more just pure mathematics. Okay, I hope I answered the vector calculus questions. Yeah, Spivak, his books are scary. Well, Spivak has a tough reputation. Has a tough reputation, especially this little book here, Calculus on Manifold. But I think his Calc 1 book, like this one, this big one, Calc 1, is actually quite approachable. This Calc 1 book is actually quite approachable. This Calc 1 is, I think, well, you can call it calculus. I would rather call it just, well, Introduction to Real Analysis, because it's virtually indistinguishable. But anyway, Spivak, that's the canonical choice, okay, for exterior calculus. Who's your GOAT mathematician? Probably, I don't know, like, it's, I figured I can't make that comment because our knowledge about mathematicians were sort of curated. You only you only read about them in secondary sources, right? I mean, the general attitude I take towards mathematicians is that I respect them in terms of their work, but because I don't know any, okay, those big names personally, I don't think much of us do. It's hard to have any sort of personal affinity towards them. Okay, I admire people like Euler, Euler went after he went blind, he was still extremely productive. Of course, that's very admirable. But you don't know their personality. Like I think I made a video about Gauss and Lejeune and their dispute about the least square method. You know, it's like after I read I read the story. I don't think I personally want to hang out with Gauss, even though I respect his work and intellect tremendously, of course. It's just that it's you got to separate the art from the artist. You know what I'm saying? But in terms of like my area of interest, I think my goat would be like Kolmogorov, the Soviet mathematician who axiomatized probability theory. So basically, Kolmogorov, in my view, is the Gauss of the was the Gauss of the 20th century, if that makes sense. Like he was probably one of the very few mathematicians who made contributions to all areas of math, like literally all. It's kind of just insane to think about Andrei Kolmogorov. So there's that. But I try to refrain from making because these are you know um, we're kind of getting we kind of I kind of want to avoid idol worshiping. These are people. They might be smart people, but they're still people. They have flaws just like us. Okay. Anyway, something somebody asked about showing the expectation of x absolute value is finite, then so is ex. Well, you can use monotonicity, no? A roof, are you still there? But yeah, let's do a little exercise. So it's quite literally one line. So prove that if the expectation of absolute value of x is finite, then so is ex. And so is ex, right? So you want to prove that. Okay, since x is greater or equal to minus x absolute value, less than or equal to x absolute value. And this is always true for any x. And then by monotonicity, of E, you can apply expectation operator on all sides. You get this, and you're done. QED. So you just use monotonicity of of the of the expectation. Yeah, idol worship is a grave sin. Yeah, yeah. We don't want to get into that. I mean, we can respect their work. I mean, but unless you know someone personally, I don't think it's wise. It's like um, uh, worshiping a movie star or something. I don't think it's any different when you make similar comments about a mathematician. They're just people. They're uh, they're accomplished people. They're still fallible. Okay, like Gauss. Anyway, so let's see. I think I managed to answer all the questions. All right, so let's continue with the examples here. All right, here, yeah. So, no worries. So, for example, we wish to estimate the true value of theta, construct small regions in omega, construct small regions in omega that are likely to contain the true value, or assess whether or not the data are in agreement with some particular theta naught, suggesting as being the true value. So here things are a little bit abstract. So what does that mean? Well, the first example, construct small regions in big omega that are likely to contain the true value. What's that? That's confidence interval. That's just confidence interval in a nutshell, foreshadowing confidence interval. Here we're not yet there yet, but this is basically confidence interval. Okay. For example, the normal distribution. If you wish to estimate the mean, the true mean, for a general normal distribution, the true mean can be any real value, right? But then if you calculate the confidence interval, it becomes a small region on the real line that is likely to contain the true value. So that's what this sentence is about. Or you can assess whether or not the data are in agreement with a particular value theta. What's that? What does this do? Assessing whether or not the data are in agreement with some particular value. That's hypothesis testing. That's hypothesis testing. It's like a pharmaceutical company claims that a new vaccine is how many times more effective, right? So, well, you take his word, you take the company's word as given, and you run a bunch of experiments. So suppose what the claim value is true, what's the likelihood, what's the probability for the observed sample to occur, right? So because the number line is densely packed, I'm not sure what that comment is directed towards. So yeah, I was talking about the two actions. First, constructing small regions in omega that are likely to contain the true value. That's confidence interval. Or in Bayesianism, a credible interval. Or assess whether or not the data are in agreement with some particular value theta. That's hypothesis testing. So these are types of inferences. But the situation here is quite different indeed. So basically that's kind of the description for statistical inference at a higher level, right? So we have statistical models, which is a collection or a family of distributions in which only one of them, one and only one of them, is the true distribution. It's the true distribution. So this is frequentism. Okay, this is frequentism because in Bayesianism there's more than one. Okay, there's no unique true probability measure. Okay, is this why you need a confidence interval? P x equals mean equals 0. Well, yes and no, I would say. Yes and no, I would say. It is still meaningful to talk about a point estimate, right? You can still say things like a point estimate for the mean is 10. Even though the probability of a sample mean equals that value is 0, that's okay. Sometimes giving, because imagine like you're working as a data analyst for for some retail company, let's just say, and they ask you to project the sales of the next quarter, and your boss is very impatient and just say, just give me a number of the projection. I don't need anything fancier. I just need one number. Okay, then you just give him a number. You always do what you're asked to do, what you're paid for, paid to do. Okay, anyway, so what I'm trying to say is a point estimate can be a meaningful statistical tool. Okay, but sometimes you wish to assess the accuracy of one estimate. Okay, or if you want to be more conservative. Okay, we want to be more conservative, and sometimes, let's say, and in certain situations, intervals are intrinsically more meaningful. Okay, so let's suppose you're designing a bridge, right? Of course, the maximum load is a critical value, is a metric, right? So you want to say the something like the maximum load is at least what? Because the maximum load, the precise value of the maximum load, the exact point where the bridge breaks, is perhaps not so useful. Okay, and in reality, you don't want to you don't want the load of the bridge to be close to that number anyway. Let's say you build a little bridge and you say, well, the maximum load is 100 ton. Okay, distributed evenly. But in reality, you still don't want to go near that number to test that limit, right? And if you go like 99.9 ton and the bridge still breaks, I mean, mathematically speaking, that's not a valid statement. But the point is, in reality, sometimes an interval estimate is intrinsically more meaningful than the point estimate. It really depends on the problem, right? So, yeah. Anyway, so here, as we mentioned, at elementary level, statistical inference consists of three major problems: point estimate, interval estimates, and hypothesis testing. And those three branches all have their own separate series and can go quite deep. Okay, but that's the main theme. It's surprising how many problems can be categorized into one of those three problems. So let's look at another simple example. Once again, you don't have too much calculations to do, so it's good for illustrating the basic concepts. Suppose we have an urn containing 100 chips, each color either black or white. Suppose further that we are told that either 50 or 60 black chips in the urn. Okay? So those are the possibilities, right? The truth is binary here. Either 50 black chips or 60 black chips. That's it. The chips are thoroughly mixed, and then 2 chips are withdrawn without replacement. Without replacement. Okay? So imagine you just grab 2 chips at once without looking at random. The goal is to make an inference about the true number of black chips in the urn. So this is kind of a difficult problem, isn't it? It's kind of a difficult problem because you only draw 2 black chips. You only draw 2 chips, and you have to make a decision based on that. So what's the decision rule here? And by the way, I just name dropped one thing: the decision rule. All the inferences is a decision rule. Okay, hypothesis testing is a decision rule. Is a procedure. Confidence interval is a decision rule. Well, normally we don't call it a decision rule because decision is binary usually or discrete. But anyway, confidence interval in more advanced literature is called a confidence procedure. It's a procedure that turns, you can think of it as a black box. It turns your data into an interval estimate. Okay, so what we mean by solving an inference problem, when we say this is a solution to the inference problem, it always means a rule, a procedure, a decision procedure, or a confidence procedure. Okay, that sort of stuff. So here, the answer to this problem, should have this form. Okay, should have this form. This is your data, S1, S2. Oh, hi, Cho. No, 2 cats. Yes, I have 2 cats. Anyway, so for all forms of data, for all possible values of data, your procedure should give an answer, whether there's 50 black chips or 60 black chips. That's your answer. So just ignoring the details of the procedure, yeah? This is what the answer should look like. Given all possible given all possibilities of the data, what conclusion do you draw? What conclusion do you draw based on each possibility? Okay, right? And those two possibilities, actually, there's only two possibilities. You're told that there's either 50 or 60 black chips in the earth. So let's think about that. Because S1 and S2 are the colors of the ith chip drawn, right? S1 is the color of the first chip drawn, S2 is the color of the second chip drawn. So your data S has four possibilities, and it's here: black, 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 white, white, black, and white, white. Right? The inference rule should say, okay, if it's black, black, then it say we have 60 black chips. For example, okay. If it's black, white, I say, okay, that's 50. White, black, that's 50. White, white, that's 50. So that's the solution. What is the epistemology regarding decision rule? Well, what is the regarding decision rule? Mathematically speaking, is a function. Is a function right here. So here, it maps a possible. It maps the set of all possible data into the set of two elements: 50 black chips or 60 black chips. Okay, so you're talking about if it's epistemology, then I can say it's empiricism. Okay, I don't want to go too deep into philosophy because I might very well be talking nonsense. Very likely I'm talking nonsense, but anyway, based on my limited reading on epistemology, there are two main schools, right? At least in the 17th century, rationalism and empiricism. So now statistics is a branch of empiricism in general because you are measuring things, right? And you're doing experiments and measuring things. So it's very much different from rationalism. Okay. A very nice question, inventive. Okay. Okay. Or you can. Well, I like nonsense. Okay. So or is and yeah, if you like epistemology, you might enjoy some good old Immanuel Kant, the Critique of Pure Reason. So basically, he tried to create a synthesis between the rationalism and empiricism, something that he calls transcendental idealism. So the idea is that our mind is structured in certain ways, that only certain forms of experiments are possible. Like he has these fancy categories about the human mind. Like your mind is only structured in a certain way that only a certain form of experience is allowed, and those form of experience aren't observed. Okay, the form of the experience are a priori knowledge when he in Kant's word. But anyway, we're getting way off topic. Coming back to probability. So here, how do we come up with such a decision? Like I gave an example earlier. So let's say I have two people, right? Say Ming and his partner. Right. So I was giving some numbers, like saying Ming likes Chinese food. 80% of the time he orders Chinese. 10% of the time he orders Italian. Another 10% he orders McDonald's, something like that. And Ming's partner, yeah, mainly empirical, exactly. And Ming's partner are a big Asian food fan, but for some reason don't like Chinese food. So she likes Korean, Japanese, and Thai. Okay. Perhaps that's too exclusive, right? So in that example, Ming and his partner don't even share any common food, which is not a great thing. So let's just say Ming's partner likes like 33% Chinese, 33% Japanese, and 33% Thai. Okay, let's just put it that way. Right. So now let's say a receipt is found in the kitchen counter, on the kitchen counter, and it's Chinese food. So who ordered the dish? Right? So you have the outcome. A dish is ordered. A Chinese dish is ordered. So who ordered the food? Right? So that's the idea. So I mean, you might want to get, well, because Ming likes Chinese food, overwhelmingly so, right? 80% of the time he orders Chinese. So you see a receipt on the counter that says Chinese food, that it's probably Ming who ordered it. It kind of makes sense. Which kind of makes sense. Of course, there's also always a possibility to make a mistake. This is the fact of life about inferences, right? But setting that aside, that's a valid inference rule. That's certainly a valid inference rule. It takes the data to a parameter, okay? So it takes the data, Chinese food, and it maps to a parameter Ming. That's the rule, right? So here, let's take a look at this example, and it's more complicated than the food example. In that case, we look at the maximum. Exactly. In that case, we look at the maximum likelihood. You nailed it, right? That's the maximum likelihood. That's the principle behind it, right? Because certain B, right? You're absolutely right. So assuming that Ming ordered the dish, the probability of observing the receipt of Chinese food is 80%. That's the first case. Or in the alternative truth, okay, Ming's partner ordered the Chinese dish. But in that situation, only 33% probability you will observe or receive for Chinese food. So what do? We pick the parameter that maximizes the likelihood of observing the data. That's exactly the ML estimator. Right. Of course, in most scenarios, the set of parameters is infinite, so maximization gets trickier. Right. But that's just technicalities, right? The principle of the statistics is quite simple in that regard. Anyway, so here, in this case, we can take the statistical model to be P theta, where theta is the number of black chips in the urn, so it's either 50 or 60. So P theta is the probability measure on your data, on the set of possible data, black, 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 white, white, black, and white, white. All right. All right, so we wish to calculate the probability for each possible outcome. Can we do so? Let's do some simple probability, shall we? What does P50 mean? Well, P50 is P theta where theta equals 50. So this is the probability. Okay, this is the probability, a probability measure. This is a probability measure. This is the probability measure over S when theta equals 50. Okay, shall we do the calculation ourselves? Okay, let's do the calculation ourselves. So here you have the urn. Two scenarios in the urn. Scenario 1. Here's the urn. Okay, you got 50 white and 50 black. The other scenario is 40 white, 60 black. Okay, and this is a set S. Black, 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 white. I just write it this way, okay? I'm not using the proper ordered pair notation because I think there's no ambiguity in there. White, black. So P50 in the case means the probability is actually 50. No. P50 is just a notation. It's just a label. P50 refers to the distribution over S when there are 50 black chips. That's the meaning. Okay, let me write things fully. Let me write things. Okay. So here, WW. There you go. So a probability measure over S is to assign a probability for each outcome so that they all add up to 1. Make sense? That's a probability measure over S. It's like a die with 4 faces. It's like a die with 4 faces, and you want to find out what's the probability for each side to occur, right? So that's the idea. So P50 is just that probability measure when there are 50 black chips in the urn. Okay, so let's do the calculation here. So this is, let's say here you have omega, or little s. Right? We write little s here. Little s. BB, BW, WB, WW. And this is P50 of S. P50 of S. So suppose that there are 50 black chips in the urn. What's the probability of, say, BB? Can we finish this table? This is a good exercise, by the way. Oh, this is something called a hypergeometric distribution. So this is something called the hypergeometric distribution, basically. So the total possibilities is 100 choose 2. And to get 2 blacks, you need to choose 2 from, well, 50 blacks. So it's 50 choose 2. And then you just simplify. Okay, so that's 50 times 49 over 2 times 100 times 99 over 2. So that's the first value. Is that clear? Okay. So, okay, hopefully this is okay. So the denominator consists of all the possibilities, all the possible ways to choose two blacks. Sorry, no, to choose 2 chips. Okay, you don't know the colors, but that's the number of total. Okay, clear, nice, awesome. So what's the probability of getting black and white then? Well, the denominator is the same, still 100 over 2. Still 100 over 2, and well, you need 1 black and 1 white, so it's 50 choose 1 times 50 choose 1. Hypergeometric distribution. So that equals to 50 times 50 over 100 times 99 over 2. What's WB? Well, WB you have, it's the same, right? So still 50 choose 1, 50 times 50 choose 1, over what? Over 100 choose 2. And then you have white. Well, so 50 choose 2, that even though the expression is the same as BB, because, well, you have 50 and 50 for each color, right? So here 50 choose 2 means choose 2 white from the 50 white. Okay, 100 choose 2 once again. Okay, so it's a good exercise to verify that these indeed add up to 1. So let's check that. Always worth checking. 50 times 49 over 2 over 100 times 99 over 2. So let's just check the numerator, shall we? So you have 50 times 49 twice. Okay, let's actually, you know what? Actually, 50 times 49 over 2 twice. You have twice of those. Okay. And then you plus, no, there's no divided by 2 here. It's just 50 times 50 and then times 2. Okay, let's calculate this number. So here you have is this equals to 4900 over 2, 2450. Okay, so 2450 plus this is 100 times 50. So 5,000. 7450. Okay. And then here you have on the bottom 100 times 99. 9900 over 2. Wait. Something is not right here. Something, did I make a mistake? 50 times 50. 50 times 250, huh? No, it's 2500 times 2. Does that look right? I want to verify all of these should add up to 1. Otherwise, it's not a valid probability measure. Huh. Things are getting a little messy. Let me redo the arithmetic. So these are supposed to be the probability measure. Okay, just want to check. 50 choose 2. Okay, 50 choose 2 plus 50 choose 1. 50 choose 1 is basically 50. Okay, 50 choose 1 is 50. So this is 50 squared. And then you got another 50 squared. 50 squared times 2. And then plus 50 choose 2. So now you have 2 times 50 choose 2, which is 50 times 49 over 2 factorial times 2. Okay, and then plus, there we go, 2500 times 2. All right. And this should equal 100 times 99 over 2, so that's 50 times 99. Okay, so here we have 50 times what? 50 times 49. There's something wrong here. There's something wrong here. 50 times 49. 2 times 50 choose 2. I think I might be missing something very obvious, but this is not right. 50 times 49 over 2. If you guys can help me out, that'd be great. But I don't think I made a mistake, no? 50 squared over 50 squared. Okay, 50 times 2. That's 50 times 100, no? It's not 50 times 99. I know these are ordered. But still they should have the same probability, no? Because in the first scenario, things are symmetric. Huh, did I make a stupid mistake? Let me check out here. So P50 assigned the probability. Okay, so this is the textbook and this is what we have. Let's compare. Where did I mess up? My goodness. P50 assigned. Right. You're absolutely right. It is ordered. That's why I shouldn't skip the ordered pair notation. You see? I ate my own medicine. Exactly. Yeah. Ramon, you're right. I mean, this notation, yeah. And so just make it unordered. Yeah, exactly. Hypergeometric distribution is for unordered. Man, You see, I was being lazy and I didn't use the ordered pair notation, so I naturally forgot things are actually ordered. But does that matter? But does that matter? It doesn't matter, no? I mean, it doesn't matter for the first case. You see, it doesn't matter for the first and the last because the two canceled out. Well, that's kind of lucky. Well, but then you think if you have BB and WW, the order does not matter, even if it does in reality, because, well, they're literally the same. So I got away with the first and last by not considering order, but what about the middle ones, huh? The middle ones are things really starting to fall apart because BW and WB are ordered, so you don't need to divide by 2 at the bottom here. Am I right? So yeah, and a sign probably exactly 50 times 50 over 100 times 99 to each of the sequence BW and WB. So order matters here because here I'm not considering order. See, in the middle, I'm not considering order. So that's why there's an extra dividing by 2 on the bottom, which is incorrect. So I ate my own medicine for being lazy. I should have used the order pair notation to remind myself, okay, BW and WB are not the same thing. Right. Actually, even if you consider them as the same thing, that's not the main issue. The main issue is that if you don't consider order, there's an extra over 2 at the bottom. Shouldn't the probability for no, no, because this is sampling without replacement, right? So if let's say BB is 0.25, so well, that's 1/4, right? So you're saying 50% times 50%, but that's not right because you're sampling with replacement. So it's not. It's close to 2.5 because we can do the calculation. Calculator, help me out. Yeah. So yeah, it should be close to 0.25 because, well, you're only taking 2 out of the 100, so it's close to with replacement, but its exact value is not, right? So that's why, right? So I think this is a good lesson to learn. I wouldn't be as shameless as say, okay, I made a mistake on purpose to, okay, I'm joking. I made a mistake, okay, and I own it. So, okay, so I got away with not considering order for BB and WW, but for the middle two, there is a real difference. So the formula I wrote is the distribution for just a hypergeometric distribution, where you only care about the combination, not the order, right? So here you have BW and WB being distinct. So you should use this way. You should calculate the probability this way. 50 times 50, because that's the first position, has 50 choices. The second position also has 50 choices. Okay, but then at the bottom you have the total possibilities to choose 2 chips. 100 times 99. Okay, so yeah, there you go. This is a big mistake. So let me just erase everything. Okay, let's erase everything. Start from a clean state. Okay, this is not good. This is not good. Okay, so here you have the urn, 50 black, 50 white. This is little s, belongs to big S. Possibilities are now in ordered pairs. BB, BW, WB, and WW. Okay, it's in my opinion the best way to write a discrete distribution. Just use a table, a row vector. Okay, and this is the probability measure P50 evaluated at scripted as little s. Okay, little s. Okay, what's BB? What's the probability for BB? Well, that's 50 times 49 over 100 times 99. Okay, what's the probability for BW? Well, that's 50 times 50 over 100 times 99. WB is the same, 50 times 50, 100 times 99. And lastly, you got the WW, which is 50 times 49 times 100 times 99. All right, let's check. Just check the numerator. 50 times 49 has two terms. 50 times 50 also has two terms. So you got what? 50 times 2 is a common factor. And then times, well, 49 plus 50. So that's 100 times 99, which is indeed the denominator. So everything checks out now. Now it makes sense, exactly. Okay? Okay, so now we're just going to compute the other scenario. We got the 60 W and 40 Y. Okay, 40 Y. All right, so here we have the same headers for the table. Okay. Use order pair notation to stress that the order matters here. All right, so this is P60. This is P60. 60 is nothing but the parameter value. It's just for bookkeeping purposes, even though here it has a meaning. Okay, P60 stands for the urn has 50 blacks. All right, but anyway, you can use P1 or P2 if you like. It wouldn't make any difference. But here are the parameters that their meaning. All right, so well, what's the first one? Well, you have 60 times 59 over 100 times 99. Well, we'll do the calculations. We'll finish the calculation and then we will do a maximum likelihood estimation. What's BW? Well, 60 times 39. No, not 39. 40. BW is 60 times 40 over 100 times 99. And WB, that's 40 times 60 over 100 times 99. W and W, that's 40 times 39 over 100 times 99. All right. So, what's the inference rule here? Well, as we said, the inference rule is another table or a function which can be visualized as a table. So, S in big S, S in big S. So these are all the possibilities for data. 4 possibilities. Okay, and the answer is just theta. Theta is in big omega. Okay. Even though I don't like this notation, big omega is canonically the notation for outcomes, but here it represents the parameter space. Yeah, excellent. Thank you very much, Certain B, for typing out the answers there. Thank you very much. It's completely correct. Awesome. So let's say we're using the maximum likelihood principle. So we're just going to pick the parameter that makes each of the outcome most likely. So now we're for the first outcome we're comparing 50 times 49 and 60 times 59. Obviously 60 times 59 is larger. Okay, so let's pick 60. That makes sense? If you're using maximum likelihood, so because the second scenario gives a higher probability for BB to occur, if we observe BB, we pick 60. That's the ML likelihood, ML estimator, okay? ML estimate, say that equals 60. All right, let's look at the second outcome. Well, you're comparing 50 times 50 and 60 times 40. So that's the first one is 2,500. The second case gives you 2,400. So the first one is higher. So you pick 50. Make sense? 50 times 50 is higher than 60 times 40. Okay? Third outcome, WB. For WB, still 50 times 50 is greater than 40 times 60. You pick 50 here. And last one is 50 times 49 versus 40 times 39. Still, 50 wins out. Okay, so this is the maximum likelihood estimate, estimator. Okay, estimator. Estimator is a random variable, which means a function. Indeed, is a function. It maps the outcome to a parameter value. Okay, so that's the maximum likelihood estimator. Okay, so well, that's the maximum likelihood estimate. What does it say overall? Okay, can we summarize it in one sentence? It says, unless you get a BB, in which case we're going to guess that the distribution is the second version, and all other observed outcomes we're going to infer that the distribution is even. Right? Make sense? So that's like a one-word summary. Okay, let's write that down. What's the summary here? We already have the function, i.e., namely, oh no. So namely, what's our maximum likelihood in verbally? Okay, sometimes in mathematics or statistics, what's going on? You want to describe the same object in the same way, in different ways. This way you reinforce your understanding. Namely, ML estimator, MLE, returns 60-40. 60 black, 40 white, if observe BB. Otherwise, returns 50 black / 50 white. So that's the output here. In all the scenarios, we're going to infer that the distribution in the urn is even. But if you get 2 blacks in a row, you're going to say, oh, probably there's more black. It kind of makes sense, no? Right, so let's see what this is, these are our steps, but here. So the choice of parameter is somewhat arbitrary, as we could have easily labeled the possible probability measures at P1 and P2. Are you writing with a mouse? Yes, I am. Yes, this is a mouse. This is not a tablet, so I'm writing with a mouse on the screen. All right. The parameter is in essence only a label, exactly, that allows us to distinguish amongst the possible candidates for the true probability measure. Yes, I just confirmed it. It is typical, however, to choose this label conveniently so that it means something in the problem under discussion. Okay. You see here, it does not give a inference rule though. You're a psychopath. I'm subscribing. Oh wow, thank you so much. Why am I a psychopath? Because I write it with a mouse? Okay, that's odd. Anyway, um, here, actually I do that all the time. Um, I just don't use pen and paper, no, sorry, pencil and paper anymore. If I want to use something equivalent, I just use OneNote and do exactly what I just did here. Okay, but anyway, everyone has their own preference. We note, I don't want AI summary, just, okay. It's hard to do, huh? No, I don't think so. I mean, it's, well, I should probably write a bit more carefully because I know the handwriting is horrible. I can do better. So anyway, we know some additional terminology in a common usage. If a single observed value, okay, so terminology, this is important because we're going to use these as standard language quite a lot. So there you go. Here we have if a single observed value for response x has a statistical model f of theta such that theta is in big omega, then a sample x1 all the way to xn. Sample means what? Sample means an IID. An IID, well, I don't want to use the word sample again, but basically a sample is an n-tuple. Okay? Is an n-tuple that each component is IID, identically independent and identically distributed. Okay, this is what we mean by a sample. Okay, so in classical statistical inference, you always have an IID sample. But if you're dealing with, let's say, time series analysis, an observed trajectory is certainly not IID. Right? So, for example, if you're, let's say, you're observing the daily average price of a stock, x1, that's the first day's average, all the way to xn. Right? You have n days of consecutive, right? You have n consecutive, I have observations for n consecutive days, so to say. Then it won't be reasonable to assume that all those observations, all those components are independent. Right? This is the classic setup in statistics. So to use the classical theory, you have to do some clever interpretation to model your data in a certain way that you have independent observations in each entry. Here, x1 might be a number, it might not be a number, so sometimes x1 itself is a trajectory. You have n independent trajectories, or sometimes you have n independent groups. So let's say you have n families. The family members tend to have certain shared common characteristics, right? They don't, let's say, if the family members tend to have similar food taste. So if you do a survey on food taste, then the family members will tend to get the same answer, most likely. Right? So in that case, you have to interpret a sample as a collection of families. If you still interpret them as a collection of individuals, then the IID assumption breaks down. So it's all a matter of applying the theory to the situation that is most appropriate. Okay? Classic theory relies on IID assumption to simplify the math. For example, here you have the joint density. It's just a product of all the marginal densities. So this is quite nice. And when you take the log, okay, the product gets converted into a sum. And once you get a sum, Well, you can apply things like the law of large numbers are dual distribution. What do you mean by dual distributions? What do you mean by dual distribution? That's not standard terminology, so I don't know what you mean. Inventive? Um, so here, a single observation has a density function, f theta, and their IID. All the sample components are IID. So the n tuple itself has a joint density given by the product of all the marginal densities, and that's it. Okay. Um, so, because I mean, I don't know what a dual distribution is. I don't think that's the standard terminology, so I can't help you out here. Okay, this it's like a Gauss distribution with two QMOS. Gaussian distributions with two components. You mean bivariate? Bivariate Gaussian distribution don't have to have independent two humps. Two humps. Okay. Gauss distribution with two humps. You mean two humps like two mode? That's not a. Okay, so that's you're talking about a mixture of a distribution. Inventive. So are you talking about a distribution that looks like this? It has two mode, right? You're just talking about a distribution like this? If yes, type yes. Okay. It's like Gaussian distribution with two humps. Well, I mean, that's just a single distribution. If you want to talk about IID, you're referring to a collection or a finite collection or a sequence of random variables. So this is just one distribution. You can call it f of x. And you can say big X follows this distribution. That's totally okay. And there are situations where this occurs. For example, in a bookstore, there, let's just say, in a bookstore there are two types of books: hardcover and softcover. Hardcover books tend to be more expensive than softcover books. Okay. So a book is either hardcover or softcover. So here, the right hump is like it's the location of the average of the hardcover books. Okay, so the x-axis is the price, and y-axis is the probability density, PD. Okay, so the average price of a hardcover book, the average price of hardcover books is around here. The average price of softcover book is around here. So in this case, x follows a mixture distribution. It's like a weighted average of two Gaussian densities. Right? And if you have m books, okay, if you have m books, randomly choose m books in the bookstore, then it is certainly possible to say those n random variables, which are prices, are IID, each f of x. IID each follows the distribution f of x. Here f of x is a two-mode distribution, a mixture of Gaussian, totally possible. Right? Here we're not saying much about the shape of the distribution f of theta. We just say, okay, that's just the distribution of a single observation. And if you have n independent observation, then the joint distribution of the sample is simply their product, the product of their density. Right? So that's it. Right? F theta can totally be a two-mode distribution. Okay, it's not dual distribution. Okay. Anyway, that's okay. We're not here to be super formal, but as long as I know what you mean, you can. I mean, I understand what you mean, and so you can now use a more commonly understood distribution. So this is called a two-mode distribution. because it's got two peaks, right? Two-mode distribution. And you can also call it a mixture of Gaussian. Mixture models are tremendously useful in practice. Mixture of Gaussian. Mixture model, mixture of Gaussian are tremendously useful in practice. Anyway, so here, this specifies a statistical model for the response x1 over xn. We refer to this as a statistical model for a sample. Nice. Of course, the true value of theta for the statistical model for a sample is the same as that for a single observation. Yes, exactly. Sometimes, rather than referring to the statistical model of a sample, we speak of the sample from the model. Okay, sample from the model. Okay, makes sense. Okay, so here you say the sample from a model. So this sentence means, okay, sample from the statistical model. The statistical model refers to the distribution of a single observation. So if you're saying a sample from the model, you're talking about an ID collection of random variables that each follows the distribution f theta. Yeah. Okay. Okay. Here's the classic notation. Whenever possible, we use uppercase letters to denote an unobserved value of a random variable, and lowercase letter to denote the observed value. So basically, in terms of set theory, right? So you're using uppercase letter for a function and a lowercase letter for the function value. Okay? Because probabilists and statisticians, they don't like writing little omega. Okay? They like to suppress the argument of a function. So to distinguish a function from its value, they use upper and lowercase letter. Okay? So even though in principle there's always a little omega as the argument of a random variable, quite often we don't write it. Okay, so here it says for the random variable use big letter, the observed value of the random variable use little letter. So this is essentially the difference between a function and the value of a function. Okay, so this is the standard notation in probability and statistics. So, average is used in all sorts of fields, including physics. Physicists can't be bothered to follow this bureaucratic rule, okay, which drives statisticians crazy. In physics, they don't even distinguish something like the sample average versus the theoretical average, the expected value versus the sample mean. So you gotta be very careful there. In statistics, things are usually quite obvious, purely based on their notation. Yeah. Once again, different objective for each discipline. All right. So, example. Here we have two manufacturing plants for machines. It's known that machines built by the first plant have life lengths distributed exponential 1, while machines manufactured by the second plant have life lengths distributed exponential 2/3. The density of these distributions are depicted as follows. Okay? And by the way, how should we interpret the distribution exponential 1? How should we do that? I think here exponential 1 refers to the exponential decay function with rate 1. So exponential 1 here, okay, has a density that is proportional to e to the minus x. E to the minus x times some multiplication or normalization constant. The second case, exponential 2/3, has a probability density that is proportional to e to the minus 2/3 x. Okay? So exponential 1 corresponds to the black curve, because it decays faster. E to the minus x decays faster than e to the minus 2/3 x. So this is e to the minus 1. And here, the dotted curve is the density for exponential 2/3. So which plant have higher quality machine? Overall higher quality machine, just based on life length alone. The second one, right? The second one, right? Because, well, it's got more machines that last longer, basically. Okay, and also you can say, there's a fact about exponential distribution that the mean is 1 over the rate parameter, or the reciprocal of the rate parameter. Okay, so for the first plant, the average length is 1 over 1 equals 1. The second plant has the average, the life length from the second plant has an average of 1 over 2/3, which is 3/2, 1.5. So on average, the second plant machine lasts 50% longer. Lasts 50% longer than the first and the product from the first plant. Okay? The densities are depicted here. Nice. You have purchased 5 of these machines, knowing that all 5 came from the same plant, but you don't know which plant. Okay. So you have a random sample, x1 to x5. And by the way, here we use little x, okay, lowercase letters, to indicate that the lifetime are all observed. Okay. And you want to make inferences about the true p. So you want to know which distribution does all these little x come from. What's the underlying data generation mechanism here? Okay. So once again, what does the final answer look like, right? The inference rule in this case cannot be listed in a table, because the possible sample now has infinitely many combinations. x1 all the way to x5, each component is now a positive real number. So we cannot possibly list them all. Right? But still, the idea is we wish to return either 1 or 2, right? Factory 1 or factory 2, from plant 1, plant 2, based on the values of the sample. So you need to come up with a rule that decides which sample maps to which plant. That's the final answer. Okay, so here we take the parameter theta to be 1, 2. So P1 is exponential 1 distribution, and P2 is exponential 2/3 distribution. Okay? So clearly longer observed life lengths favor theta equals 2, which makes sense, right? So as we said, well, actually this is exponential 1.5. You see, this is kind of annoying because this is inconsistent notation. Here it says, because exponential distributions are especially annoying, sometimes the parameter, the number in the bracket of exponential distribution refers to the rate parameter. So 2/3 here obviously means, by obvious I mean by looking at the picture, 2/3 refers to the rate parameter because the curve 2/3, the curve with a parameter of 2/3 decays slower. Right. So that's a rate parameter, but somehow here it changes to 1.5. Sometimes exponential distributions are also parameterized by their mean. For exponential 1, the mean and the rate parameter have the same numerical value, so it doesn't matter. But here you see this is exponential 2/3, this is exponential 1.5, so that's a typo here. So that's the inconsistency. You know what? It's always easier to point out other people's typos and inconsistencies than your own. I'm just ashamed by the amount of typos and inconsistencies in my own uploads and posts. It's ridiculous. I mean, how could I miss that? I mean, it's always easier to point out other people's mistake, right? So I was at the worship today because it's Sunday, and the priests were talking about the Pharisees. They know the scripture well, and they always criticize other people. You know, I might be a Pharisee because I can't spot my own mistake. I'm super sharp. I'm kind of, oh, here, see the inconsistency right here, exponential 2/3, exponential 1.5. Anyway, so, but anyway, so here, P2 on average is bigger. Okay, even though that's not a very rigorous statement. Basically, it says for the population P2 for the second plan. Okay, P1 can mean, well, it literally means the distribution exponential 1, or you can interpret as the population for the machines coming from plan 1. P2 comes from the second probability distribution exponential 2/3, right? So that's the second distribution. Right? So longer lifetime favors P2. So if your machine, they all tend to last pretty long, it's very likely that it's come from the superior plan, plan 2, right? So for example, if x1 to x5 equals 5, 3.5, 3.3, 4.1, 2.8, you see, so they're all greater than the average, huh? For theta 2, the average is 1.5, and they all exceeded that. So it's intuitive that we're more certain that theta equals 2 than if, say, x1 and x5 is 2, 2.5, 3, 3.1, 1.8. Okay, but this is like a super neat example because all the components x1 and x5 have a strict order. You see, x1 is greater than the x1 here, x2 here is greater than the x2 here, blah, blah, blah. But in reality, it won't be quite so neat. Okay. So anyway, we're not even now introducing a single criteria, even though we sort of did it here, the maximum likelihood estimation, which is quite intuitive. But here it's not clear how do we assign the maximum likelihood estimator, no? It's not that clear. Or is it? Or is it? Let's do the math. Okay, so let's do the math and see, can we come up with just apply the same principle for this little example. So you have theta 1 equals 1, theta 2 equals 2/3. How do I write that? Yeah, 2/3. It's 11:30. I'm kind of getting tired, so I might call it a day real soon. Let's just finish up this example. So how do we do the maximum likelihood estimation for this example? Well, let's first define the likelihood function. Okay, just write that down right away. The likelihood function is the product, or should we say, just say the joint density. It's just the joint density of 5 observations, I from 1 to 5, f with the parameter theta, okay? F with the parameter theta xi. And by the way, here, because we're using the exponential distribution as a model, f theta of x is what? Here theta is a rate parameter, so for rate parameter density looks like this. Theta times x to the minus, sorry, not say x, but e to the minus theta times x, where x is positive. All right, so that's the exponential density. Okay, so if we plug in that formula, we get the product of theta times e to the minus theta xi, like so, and then we simplify, okay, and we get theta to the 5. Theta to the 5 times e to the minus theta times the sum I from 1 to 5 xi, like so. Okay, so even though the likelihood function is numerically the same as the joint density, you see, this formula right here says the likelihood function L theta equals the numerical value of the density. But they're fundamentally different objects. The likelihood function treat the parameter theta as a variable, whereas in probability theory, the parameter theta is treated as a constant, whereas the xi's are the variables. Okay, so here little x is considered fixed, right? Using our notation, by our convention, little xi stands for observed values of the random sample. So the variable is theta here. All right. So because here we only have two values, theta 1 and theta 2, we can consider the ratio. And by the way, this is a super important idea called the likelihood ratio. Right? If you guys have seen some hypothesis testing, you might have came across with the method likelihood ratio test. A likelihood ratio test, and it has some nice properties. In this scenario where you only have two alternatives, the likelihood ratio test is actually a so-called most powerful test. Most powerful test. So, I mean, I don't want to get into the technicalities of hypothesis test right now because we're getting to the end, and hypothesis testing definitely needs its own separate video or live stream. But here, because it's intuitive that we only have two candidate parameter, right? And if you just wish to compare L of theta 1 and L of theta 2, you can just take the ratio. Right. So L of theta 1 over L of theta 2. Okay. So let's first use the general notation, and then finally plug in theta 1 equals 1, theta 2 equals 2/3, all right? So that's the ratio. See if then there's anything we can simplify. So on top we only have theta 1. At the bottom we have theta 2. All right? Okay. So we wish to come up with a decision rule that favors theta 1 or theta 2 based on the xi's we observe. Okay, so let's do the algebra here. So you have theta 1 over theta 2 raised to the 5, theta 1 over theta 2 raised to the 5th power. Oh, sorry, I forgot to change the subscript here. All right, so that's what? The exponential can be simplified to e to the minus theta 1 minus theta 2 quantity times the sum of xi times the sum of xi. Okay, so when is this thing greater than 1, huh? Well, let's just set this to be greater than 1. Let's set the likelihood ratio to be greater than 1. When this is greater than 1, of course, this favors theta 1, i.e. favors theta 1. Data favoring theta 1. All right. So you just get an inequality like so. Okay, because remember what we want here. We want a decision rule based on the values of xi's. So let's just manipulate this inequality so that the left-hand side consists of only data point and the right-hand side consists of theta 1, theta 2, and whatnot, right? So here we have, just do some simple algebra. The exponential is greater than theta 2 over theta 1 raised to the 5th. All right. Then you take the log minus theta 1 minus of theta 1 minus theta 2 quantity times the sum of xi is greater than, all right, is greater than the natural log of the right hand side, which is 5 times the natural log of theta 2 over theta 1. Okay? And then you isolate what? You isolate the sum of xi. Isolate the sum of xi, which is greater than, I guess this is, yeah, so we can write it this way, 5 times, well, theta 2, natural log of theta 2 minus the natural log of theta 1. I'm just trying to make things a little bit nicer, okay, over theta 2 minus theta 1. Okay? And let's divide by 5 on both sides. So you get a nice expression. This is x bar. So this is our decision rule here. So this is a decision rule. Right? We have theta 1 and theta 2, so you can calculate the right-hand side. So you can calculate the right-hand side. So this says the inference rule. The inference rule. So data favors, or should we say not data favors, but MLE. The MLE, maximum likelihood estimator, returns what? Returns 1. Returns theta 1. If x bar is greater than the average of the life length is greater than this value, and returns theta 2 if otherwise. If x bar is less than that. And you can do some algebra here. So if we plug in theta 2 equals, actually let's draw a little picture. What does this mean? What does this mean? So this is a natural log function. Okay, theta 1 is, theta 1, theta 2 is shown as follows. So this is the slope of the secant. X bar is meant to compare with the slope of the secant. It has a nice geometric interpretation. That's why I rearrange it this way. So substitute theta 1 equals, I'll finish up this part and we'll call it a day. Theta 1 equals 1, theta 2 equals 2 thirds. Anybody still watching? I can't see how many people watching on OBS. That should be a way, but oh wow, there's 15 people. That's insane. My goodness. I thought everybody's gone. because I can't see it on my OBS. I had to open up my phone and see. Anyway, substitute theta 1 equals 1 and theta 2 equals 2. Okay. So that's your final answer? No, so not 2, but 2/3. Yeah, still watching. That's crazy. That's insane. Okay, here, and just do the algebra real quick. The natural log says natural log of theta 2, 2 over 3, taking the natural log, minus 1. Yeah, good show. Long math streams, thanks. What are we doing? Beard? We are doing statistical inference. Right here, this book. Okay? This book. We're doing statistical inference. Okay, come on. Yeah, chapter 5. Okay, we sort of started from chapter 5 actually. We didn't do all the previous chapters. The previous chapters are all probability. Here is statistics proper. So we're trying to understand what does statistical inference mean. Okay, and even though we're not technically officially entered the maximum likelihood chapter, we are doing because this is so intuitive, such an intuitive method. We favor the parameter that gives the higher likelihood for the data to occur. So now, in this example, you are sampling from one out of two possible exponential distribution, and you have to decide what is the true distribution. So what do? We set up the likelihood function. And then we compute the likelihood ratio, because in this case there's only two alternatives. So comparing which parameter gives the larger likelihood value is very easy, and then we just simplify. Okay, and we're near the end of the stream. Okay, natural log of theta 2 is this, minus the natural log of 1, which is 0, divided by 2/3 minus 1, 1.21. Okay, 1.22. Okay, so the MLE returns theta 1 if x bar is greater than 1.22. That makes sense? It does, right? It sort of does. Because remember, as we said earlier, if overall the machines have a higher lifespan, it favors theta 2. Because for theta 2, the average is 1.5. For theta 1, the average is 1. Here, the empirical, what the inference rule says, if the empirical average is greater than 1.22, we pick theta 1. Hang on, that makes no sense. Wait. Wait. This is messed up, huh? This is messed up. What? This is, okay. Going back, algebra. Did I make a mistake? Theta 1 over theta 2? Theta 1 over theta 2? You see here, this is where things are problematic, because I divided by this number on both sides without considering the sign here. Vernon, this is, yeah, I commented on that. The 1 versus 1.5 thing. I commented on that. So, yeah, this is an annoying thing for exponential distribution. Let me just give you the Wikipedia page. Exponential distributions you kind of sort of have to interpret the meaning of the parameter yourself. Okay, because the exponential distribution has two equivalent ways to parameterize them. Sometimes you can use the rate parameter. If you use the rate parameter lambda, the density looks like this. If you use the alternative parameterization, namely the mean, the scale parameter, beta, by the way, 1 over lambda is exactly the mean. You see? The mean is 1 over lambda. So the alternative parameterization uses the mean to parameterize the same distribution. So in the book, it uses both. Come on, make a choice. You see, here it says exponential 2/3, but here it says exponential 1.5. So that's kind of messed up, huh? But based on this graph here, we can tell the dotted curve, which is exponential with greater mean, should be exponential 2/3. Because the other one, the black curve, you see, it intersects the y-axis at 1. Exponential 1, doesn't matter 1 is the rate or the mean, its density is e to the minus x, which intersects the y-axis at 1. So we are certain in either form of the parameterization, the black curve is exponential 1. So the dotted curve has to be exponential 2/3 or exponential 1.5. But exponential 1.5 is supposed to be the exponential distribution with a greater mean. See, here the dotted curve has a greater mean. It has a greater mean. So here at 1.5 means the average, okay, or the expected value of the exponential distribution. And here 2/3 is the rate. This and this are actually the same thing. Because of the annoying alternative parameterization for exponential, okay, so this is an inconsistency. You either pick the rate parameter or the mean parameter. Okay, so what happened here is I made, yeah, I see, okay, this is a sloppy mistake. This is a sloppy mistake because I just divided theta 2 minus theta 1 on both sides without any regard about the sign. You see, if theta 1 minus theta 2, so this is, okay, theta 2 minus theta 1. If theta 2 minus theta 1 is positive, then you don't change the sign. Here, we just leave the inference rule like so, because we don't know the sign of theta 2 minus theta 1 in a general case, right? So I don't like this anymore. I don't like this anymore. So instead, and I don't like this picture anymore, because, okay. So instead, we're just going to write theta 2 minus theta 1 times x bar greater than the natural log of theta 2, or let's just put it this way, natural log of theta 2 minus the natural log of theta 1. Okay, this is the valid decision rule. So here, if we plug in these values, let me just modify the final answer real quick. Put less than, okay. So substitute theta 1 equals 1 and theta 2 equals 2/3. The MLE returns theta 1 if x bar is less than 1.22. Because in this case, theta 2 minus theta 1 is negative. Okay, here. Return theta 1 if the first inequality holds, right? Theta 2 minus theta 1 is negative 1/3. So when you divide by negative 1/3, the inequality sign flips. Okay, and returns theta 2 if x bar is greater than 1.22. So now it makes sense now. Right? So now it makes sense now. So higher average correspond to theta 2. Lower average correspond to theta 1. Right? The theoretical mean for p theta 1 is 1. The theoretical mean for theta 2 is 1.5. So 1.22 sort of sit in the middle. Intuitive, right? It makes sense, right? So I hope this little example deepens our intuition about maximum likelihood estimates even better. Because so far, what are the common characteristics? In this very session on mathematical statistics, the parameter choices are finite. Well, we only seen two examples where the parameter choices are binary. Right? Here in this example, the parameters is either 50 black chips and 60 black chips. Right here, the two parameters for the exponential distribution are also binary. And I also give a simpler example earlier. Food ordering, two-person. Okay, two persons each have their own food preferences. Okay, so in that case, the parameters are each person. Okay, so we will. Let me just go into the spoiler a little bit. If we go to, I think it's in optimal inference, I believe. Let's go to optimal inference. So let's say if you only have two alternatives, then what we did right here, the likelihood ratio thing is actually optimal. So you can't do any better than that. Okay, let's go back to, that way this is chapter, I think chapter 8, yeah, this is chapter about optimal inference. There's something called the Neyman-Pearson lemma. Yeah, so, I mean, if you only have, okay, if you only have the Neyman-Pearson theorem, Neyman-Pearson theorem. So basically, it says, if you only have two alternatives, omega equals theta 0, theta 1, and you want to test theta equals theta naught versus the alternative, well, the alternative would be theta equals theta 1. Here you have some terminologies, but basically says, okay, the UMP seems uniformly most powerful. So this is optimal in a sense. So what do we mean by that? When you do hypothesis testing, here even though we're solving an estimation problem, because the parameter you wish to estimate only can take two values, so it's indistinguishable from hypothesis test. If that makes sense. The parameter only has two values. The hypothesis test only, you make a binary decision as well, so it's equivalent in this regard. So here there's a theorem that says the optimal test, the exact meaning of the optimality have to be introduced later, but basically it says the optimal test has this form. Okay, the deciding quantity is the ratio between probability density, which is exactly what we did here. The ratio between probability density. So this is actually the optimal test, the optimal inference procedure here. Anyway, thank you very much for watching. It's getting 12 a.m. here. I'm very tired now. So I'll see you guys next week. Actually, tomorrow there's a stream. If you guys are interested, I'm going to stream abstract algebra on my 2.0 channel. So the point of that stream is to showcase my first attempt on the subject. Okay, I've emphasized that very many times. I don't know algebra very well. My background in algebra is just standard linear algebra courses. That's it. I have never taken a formal abstract algebra course in my university. I never did. But I always wanted to learn more. Well, since after I did university. What time? Well, it's 7 p.m. Eastern Standard Time. Thanks, Smiley. Thanks for listening. Have a good night. Thank you, Bengal CS. Thanks a bunch. No, um, thank you, John. So I was saying that the point of the stream for the abstract algebra is not only to showcase the math. Where's the channel? It's just math with Ming 2.0. Remember, my channel got hacked, so I started the 2.0 channel. Yeah, can I put down the link for sure? Yeah, just go to YouTube and search Math with Ming 2.0. I'll do that and put it in the chat here. The same avatar, same profile picture, okay? Hang on. You just put it in OBS. Yeah, that's the 2.0 channel. I mean, it's got no new videos there. I have some re-upload. They say that if you can teach something to strong evidence, you understand it. Well, thank you, Inventive. I would say for the statistics stuff, the book that we showcased today, I know at least 90% of the stuff. Perhaps I should put a 2.0 in the new profile picture for the, because you know the 2.0 channel was started in a time of sheer desperation. Okay, it's the same banner. It's just the name is different. This channel was started when I didn't even know if I'm going to get the main channel back, because that was gone. Okay. So I started the 2.0 channel while the main channel was down. And here on the 2.0 channel, we sort of do things that aren't particularly fit the main channel's main themes, you know, and it's more for like experimental stuff. So here, now that the main channel is back, the 2.0 channel is more for the experimental stuff like the abstract algebra first attempt series. Basically, I'm doing this to answer a common question: how do you self-study? Well, that's how I self-study. Right? So if you follow that, I won't promise great insight in abstract algebra, but it will showcase what topic in abstract algebra we're doing focus tomorrow. Ring and field. Ring and field. So last time we did the definition of a group. Okay? And tomorrow we'll get to the definition of field. It might be good to have a Rumble channel in case you got completely nuked off. Yeah, exactly. So here tomorrow we'll do the definition of a ring, and it's also based on free notes. Okay, free notes. It's a course from University of Waterloo. There you go. This is the notes we will be following. It's in the link. Okay, so last time we did most of the chapter 1, I believe, which is introductory chapter. The most important component being the definition of a group. So we know what a group is. Chapter 2, introduction to ring. So tomorrow we'll do introduction to ring. Yeah, just write 2.0 over your picture. That's right. That's right. Otherwise it gets confusing. Same profile picture. Yeah. So we'll do introduction to ring tomorrow. Like if you are interested in how I approach a subject for the first time, I won't promise any great insight because it's the first attempt, right? Right. So it's not like when I read a statistic book, I already see this is what's coming next. I can't do so for abstract algebra. But I guess that's also kind of the point, right? Just the raw, unfiltered procedure of self-study, and sometimes with great frustration, and that's just part of the process. But without so, we cannot learn. That's the thing. Like you cannot expect some fancy visualization to do the thinking for you. Right. So anyway, so yeah, that's tomorrow's stream because I was planning to have the alternative stream in the morning on Sunday, but I couldn't do so. So yeah, that's why it got rescheduled to tomorrow evening. Okay, 7 p.m. Eastern Standard Time. Okay. Anyway, I really gotta close this. Thank you guys very much for watching, and I'll see you next time. Bye.